You have probably seen the photograph. A tiny square of sky no wider than a grain of sand held at arm's length, and inside it 10,000 galaxies, each one a city of hundreds of billions of stars. The photograph makes it look crowded. That is the lie. The nearest large galaxy to our own sits 2.5 million light-years away. If you scaled the Milky Way down to the width of a dinner plate, that neighbor would be across the room maybe 15 feet from where you're sitting right now. That already sounds like a lot of empty space. But the nearest galaxy to us is also, by the standards of the universe, right next door. Between most galaxies, between the overwhelming majority of galaxies, the separation is not 15 feet. It is the length of a football field, a city block, a small country. We are going to move through that space together, honestly, slowly. If something tonight stayed with you, some small thing that made the universe feel a little closer, a like or a subscribe would mean a lot to me. Not for any number, just so I know you were here. Now, let us begin. Start with something you trust. You trust your eyes. You have trusted them your entire life to judge distance, to measure closeness, to tell you whether something is near enough to touch or far enough to ignore. That trust was built on a few 100,000 years of evolution on a single planet, navigating distances that topped out at a few thousand kilometers on a clear day. Your visual system is extraordinary at what it was built for. It was not built for this. In 1995, a telescope in low orbit was pointed at a patch of sky in Ursa Major, a region with no known stars, no known galaxies, no visible anything. Astronomers chose it precisely because it looked empty. The exposure lasted 10 days. When the data came back, that empty patch of sky contained roughly 3,000 galaxies, each one at a different distance, each one separated from its neighbors by gaps that the photograph collapsed into a flat field of light. The image is beautiful. It is also, in a specific and important way, misleading. A photograph flattens everything. Two galaxies sitting near each other in the frame feel like neighbors, and some of them are, but many pairs that look adjacent are separated by hundreds of millions of light years. Cross that gap at the speed of a commercial aircraft, and the journey takes roughly 200 trillion years. The universe is about 14 billion years old. You would need more than 14,000 universe lifetimes just to cross what looks, in a photograph, like a small gap between 2 points of light. Your eye reads them as close. They are not close. But they are not close. There is a second layer to this. Photographs of space are not just compressed in depth, they are compressed in time. The galaxies in that deep field image are not all being seen as they are now. The light from the nearest ones left perhaps a few 100 million years ago. The light from the most distant ones left when the universe was less than 1 billion years old, when those structures were still forming, still chaotic, still nothing like the organized spiral arms we see in younger galaxies. The photograph layers 13 billion years of cosmic history into a single flat image. You are not seeing a neighborhood, you are seeing a cross-section of time. That is worth pausing on. When you look at a deep field image, you are not seeing space. You are seeing the history of space, stacked like geological strata, with the oldest material at the back and the most recent at the front. The fact that it looks like a single moment, a single room full of galaxies, is an artifact of how photography works, not a property of the universe itself. Now take that correction and extend it. The observable universe contains roughly 2 trillion galaxies. 2 trillion is not a number your intuition can grip. So try this. If you counted 1 galaxy per second, without sleeping, without stopping, it would take roughly 63,000 years to count them all. If you started counting on the day the first anatomically modern humans walked the African savanna, you would still be counting now, and you would not be close to finished. 2 trillion galaxies. And in photographs, they look packed in. They look like something you could navigate, like a city with very wide streets. The streets are not wide. The streets are almost incomprehensibly empty, and the buildings are almost incomprehensibly far apart, and even that framing fails. Because a street implies continuity, implies that you could in principle walk from one side to the other if you had enough time. You cannot walk these streets. The universe will not permit it. Not because the distances are merely large, but because the distances are actively growing. The space between galaxies is not static. It is expanding. Not the galaxies moving through space, the space itself stretching, adding new distance between every point in the universe with every passing moment. A gap that is 2 million light-years today will be larger tomorrow, not by much, not by anything you could measure in a human lifetime, but compounded over billions of years. This expansion does something more than make the universe bigger. It makes portions of it permanently unreachable. The light we receive from the most distant observable galaxies left those galaxies when they were much closer than they are now. While that light was traveling toward us, the space it was crossing was expanding beneath it, the way a swimmer crossing a river gets pushed downstream even while swimming straight across. The galaxy that emitted that light is no longer where the light says it is. It has been carried far beyond what we can see. More than that, roughly 94% of the galaxies in the observable universe are already beyond a threshold called the cosmic event horizon, the distance beyond which any signal we send today will never reach its destination, because the expansion of space is carrying those galaxies away faster than light can cross the growing gap. Not faster than light travels through space, faster than the space between us and them grows. The galaxies on the other side of that horizon are not violating any speed limit. The road between us is simply lengthening faster than anything can traverse it. The photographs do not show you this. The photographs show you light that arrived. They cannot show you the 94% that is already gone, already locked behind a boundary that no future technology will cross, no matter how advanced, because the boundary is not an engineering problem. It is a property of how space itself behaves. Every century, more galaxies slip past that horizon. Not dramatically, no flash, no edge, no visible departure. They simply recede to the point where the light they emit will never close the gap between us, and then they are gone from the reachable universe in the most complete sense of that word. Not hidden, not blocked, gone. The light we still receive from them is a record of what they were, a fossil of a connection that no longer exists in any functional sense. There is something worth sitting with here, not as a philosophical exercise, but as a plain statement of physics. Every human project involving those galaxies, every imaginable mission, every signal, every attempt at contact across that distance was foreclosed before it began. Not by lack of ambition, not by lack of technology, by the geometry of space-time itself, which expanded in a specific direction at a specific rate and drew a line that observation can cross, but nothing physical ever will. You are looking at the universe through a window, and the window is slowly, permanently closing. The question that follows is not how to reopen it. The question is what it means that we can see so clearly into a space we can never enter, and whether the act of seeing, without the possibility of reaching, is enough. There is a number that took me a long time to stop treating as just a number. 100,000 years. That is how long it takes light, not a spacecraft, not a signal we could amplify, not something we might someday improve upon, but light itself, moving at the fastest speed anything in the universe is permitted to travel to cross from one edge of our own galaxy to the other, not to the nearest star, not to the center. From one rim of the Milky Way to the opposite rim, a beam of light needs 100,000 years. To cross the room you are in right now, light needs about 10 nanoseconds, less than a blink, less than a nerve impulse. The Milky Way is not a room. If you wanted to travel that distance 100,000 light-years in a commercial aircraft, flying without stopping, the journey would take approximately 1 trillion years. The universe itself is only about 13.8 billion years old. You would need to travel for roughly 70 times the current age of the universe to reach the other side of the galaxy you already live inside. And yet, by cosmic standards, the Milky Way is not particularly large. There is something disorienting about this that I want to stay inside for a moment, because the numbers alone don't carry it. The Milky Way is our home. Everything humanity has ever done, every civilization, every war, every piece of music, every person who has ever lived, all of it happened within a region so small, relative to this galaxy, that it doesn't register on any map drawn at galactic scale. Our entire recorded history, roughly 5,000 years, is less than 1/20th of the time it takes light to cross from the outer Perseus arm to the far edge of the Scutum Centaurus arm. We have not had time to send a message to the other side of our own home and wait for a reply. Not because we haven't been trying, because we haven't existed long enough. The Milky Way has a structure worth understanding, because its scale becomes stranger the more precisely you hold it. The galaxy is a flattened disk, roughly 100,000 light-years in diameter and about 1,000 light-years thick at our location. At its center sits a dense bar of older stars, about 27,000 light-years long. From the ends of that bar, spiral arms unwind outward, not solid objects, but regions of slightly higher density where gas collapses into new stars, then moves on, leaving the arms shape behind like a traffic pattern that persists even as the individual cars pass through. Our solar system sits in a minor branch between two of those arms, the Orion Spur, about 27,000 light-years from the galactic center. Not at the edge, not at the core, but in a relatively quiet region, which turns out to matter for reasons that have nothing to do with comfort and everything to do with survival. The galactic center is violent. Dense radiation, competing gravitational fields, stars packed close enough that planetary systems become unstable over long timescales. The outer edge is too sparse for the heavy elements that planets like Earth require. Our position is almost suspiciously suitable, the kind of coincidence that looks like intention until you remember that we are only here to notice it because it worked. The entire solar system orbits the galactic center once every 230 million years. That unit of time has a name: a galactic year, sometimes called a cosmic year. In the time it takes the Sun to complete one orbit around the center of the Milky Way, the following happened. Dinosaurs arose, ruled, and vanished. Every species alive today either evolved or went extinct. The continents, which were already rearranged from where they had been a galactic year before that, rearranged themselves again into something approaching their current configuration. The last time the Sun was in roughly this position in its orbit, there were no birds, no flowering plants, and no mammals larger than a house cat. We have completed perhaps 19 or 20 of these orbits since the solar system formed. The galaxy itself has been rotating for far longer. The oldest stars in the Milky Way's halo, the spherical cloud of ancient stars and dark matter surrounding the disk, are more than 13 billion years old. They formed when the universe was less than 1 billion years old, before the spiral structure of the galaxy was fully assembled, before the disk took its current shape. Those stars are still here, still orbiting, in paths tilted at steep angles to the disk, remnants of a time when this galaxy was something different, looser, hotter, less organized, and the spiral arms we live in had not yet wound themselves into existence. The light from those ancient stars, the ones in the halo, left them thousands of years ago. What we see when we observe them is not what they are now. It is a record of what they were when that light departed. All of astronomy works this way. Every observation is a fossil of a past moment, arriving now, read as present. The further you look, the deeper into the past you see. There is no way to see the Milky Way as it is right now. No way to see any of it simultaneously, because light has a speed and the galaxy has a size, and those two facts together mean that the word now has no clean meaning at galactic scales. By the time light from the far side of the Milky Way arrives here, 100,000 years have passed. Whatever is happening over there at this moment, if this moment even means anything at that distance, we will not know about it for 100 millennia. The galaxy you live in is a place you will never fully see. Not with better telescopes, not with more time. The scale of it guarantees that its presence is permanently hidden from any observer within it. This is not a limitation of our instruments. It is a structural feature of reality, a consequence of light having a finite speed and space being genuinely large. The universe does not give you simultaneous access to its own contents. It gives you a layered record, older the further you look, and no amount of technology changes that constraint. I find something clarifying about this in a way I did not expect when I first spent time with it. The Milky Way is not a backdrop. It is not a setting. It is an object with its own deep history, its own ongoing processes, its own future, and most of it is happening completely beyond our awareness. Not because we are small, but because information takes time to travel and the distances are real. The nearest star to our Sun, Proxima Centauri, is about 4.2 light-years away. A signal sent there today would arrive in 4.2 years. A reply would reach us 8.4 years after transmission. That is the fastest conversation the universe permits with our nearest neighbor, an exchange with a minimum round-trip time of 8 years, assuming something there received and responded immediately. Proxima Centauri is practically next door by galactic standards. It sits about 1/40,000th of the way across the Milky Way. 100,000 light-years of mostly silence, stars separated by years of travel time each, gaps between them where almost nothing exists, not vacuum in any everyday sense, but something genuinely close to nothing, where a cubic meter of space might contain one atom or fewer. The Milky Way is not a dense place. It only looks dense because photographs collapse the depth, and our eyes are built to notice the light, not the dark. What fills most of the Milky Way is the same thing that fills most of the universe: distance. And outside the Milky Way, outside this 100,000 light-year disk we call home, the distances do not get smaller. They get larger by a factor that the word larger was not built to hold. Step outside on a clear night, away from city light, and let your eyes adjust for 10 or 15 minutes. At some point, if you are in the northern hemisphere and you know where to look, a faint smudge will appear in the constellation Andromeda, slightly above and to the left of the Andromeda star itself. Not a point, not a spark, a smudge, soft-edged, diffuse, about the size of 6 full moons, laid end to end across the sky. You are looking at 2.5 million light-years of distance with your naked eye. Every photon reaching you from that smudge left its source before the genus Homo existed, before the first stone tool, before any human hand shaped anything. The light that entered your eye tonight departed when the ancestors of our species were still something else entirely, smaller-brained, fur-covered, living in African forests, with no capacity to look up and wonder about the source of that light. Those photons have been crossing intergalactic space since before we were us. And Andromeda is, by every cosmic measure, close. That is the fact that breaks something in ordinary thinking, if you hold it long enough. Andromeda is our nearest large galactic neighbor. It is practically adjacent in the structure of the universe. The gap between us and it, 2.5 million light-years, is considered a local distance, a neighborhood crossing. Astronomers group the Milky Way and Andromeda together in the same structure, the local group, because gravity still loosely connects them. They belong to the same family. And the light from this family member takes 2.5 million years to arrive. Try to cross that distance at the speed of our fastest spacecraft, the Parker Solar Probe, at its closest approach to the Sun, moving at roughly 690,000 kilometers per hour, and the journey takes approximately 4 billion years, not 4 billion days, not 4 billion months, 4 billion years. The Earth formed about 4.5 billion years ago from the debris around a young star. The entire geological history of this planet, the Hadean Oceans, the first bacteria, the Cambrian explosion, the dinosaurs, the ice ages, the emergence of humans, every civilization that has risen and fallen, all of that history fits comfortably inside the travel time to our nearest galactic neighbor. You would arrive at an empty destination. Not empty because Andromeda would be gone, empty because the Sun would be gone, the Earth would be gone. The civilization that built the spacecraft would be separated from its own launch by a span longer than the current age of the planet. Whatever was waiting at Andromeda would have no way of knowing who sent it, because the senders would be as remote in time as the first single-celled organisms are to us now. There is a specific quality to this kind of distance that I want to try to describe carefully, because it is different from just being very far away. When something is far away, the implicit assumption is that the distance could in principle be crossed with enough time, enough resources, enough will. We are far from the moon, but we went there. We are far from Mars, but missions are already designed. Distance ordinarily implies traversability, even if difficult. The distance to Andromeda breaks that assumption entirely. It is not a challenge to be overcome. It is a structural feature of the universe that closes off a class of possibility. No biological creature can make that journey, because no biological creature lives long enough. No civilization can make it in a single continuous effort, because civilizations do not persist for 4 billion years, and even if one did, it would be so transformed by that duration that calling it the same civilization would be a category error. The journey is not difficult. It is categorically impossible for anything continuous with us. Now float outward. Leave the Milky Way behind. Leave its 100,000 light-years of stars and dust and ancient globular clusters. Rise above the galactic plane until the disk becomes a thin, bright lens below you, and then keep going. At 1.25 million light-years out, roughly halfway between the Milky Way and Andromeda, something changes. Every direction looks the same. Not almost the same. The same. In every direction. Darkness. No galactic disk visible behind you. It has shrunk to a faint smear of light, smaller than a thumbprint, already requiring effort to locate. Nothing ahead. Andromeda, still 1 million light-years distant, not yet bright enough to dominate the view. Above, below, left, right, forward, back, blackness. Pierced occasionally by the remote sparks of other galaxies hundreds of millions of light-years away in every direction. No stars, no dust, no gas worth naming, perhaps 1 atom per cubic meter of space, scattered so thinly that the concept of gas barely applies. No sound, of course, but more than no sound. No medium in which sound could exist. No substrate of any kind. Nothing for a signal to propagate through. Nothing for heat to conduct through. Nothing for a body to push against. The instruments you brought would sweep through cubic kilometers of space without recording a single particle impact. You would not be cold in the familiar sense. Cold requires a medium that can drain heat from you: air, water, metal. In this environment, there is no medium. You would lose heat only by radiation, slowly, at a rate determined by your temperature relative to the cosmic background radiation, which sits at roughly 2.7 degrees above absolute zero. Your body would radiate heat into almost nothing, and almost nothing would radiate back. The process would be very slow, but the isolation would be total. No surface anywhere within 1,000,000 light years. No gravity source strong enough to feel. Nothing to orient toward. There is a question that emerges from this place. If you sent a signal from here, a radio transmission, aimed at the Milky Way, how long would it take to arrive? 1,250,000 years. And if someone received it and replied immediately, the reply would reach you assuming you were still there, still waiting 2.5 million years after you sent the first transmission, by which time the Milky Way you were trying to reach would have changed in ways no model can predict in detail. The stars would have drifted, the spiral arms would have rotated. The civilization that received your message, if any existed, would be separated from the one that sent it by a gulf of time larger than the entire existence of our species on this planet. The isolation at that midpoint is not a feeling. It is a physical condition, as real and as measurable as pressure or temperature. There is something here that takes a long time to fully absorb, not the distances alone, but what they say about the universe's fundamental indifference to connection. The universe is not hostile to connection. Hostility implies intent. The universe simply has a geometry, and that geometry makes certain things possible and certain things not. And contact between civilizations at intergalactic distances falls cleanly into the second category. Not because we are too small or too slow, but because the distances are genuinely this large and light genuinely travels at this speed, and nothing has found a way around that constraint. We are not isolated because something went wrong. We are isolated because this is what the universe looks like at large scales. The smudge of Andromeda, visible to the naked eye on a clear night, is perhaps the most honest object in the sky for this reason. It looks close enough to see without instruments. It is close enough, by galactic standards, to belong to our local family. And it will take 4 billion years to reach at the fastest speed we have ever achieved. Both things are true at the same time. The nearness and the unreachability occupy the same object, and neither cancels the other out. The word empty does not have enough gradations. In ordinary use, empty means a room with no furniture, a glass with no water, a parking lot at 3 in the morning. These are all versions of empty that still contain air, roughly 10 trillion molecules per cubic meter, each one moving, colliding, transferring heat. Even a room we call empty is, by any physical measure, densely packed. Step outside the Earth's atmosphere, and the density drops to almost nothing, a few hundred molecules per cubic meter in low Earth orbit, still falling. In the space between stars, roughly 80,000 particles per cubic meter, about 10 trillion times less dense than the air in your lungs right now, yet still measurable, still present, still enough to carry the sun's pressure waves outward and for a spacecraft to record the difference. Cross out of the Milky Way entirely past the outer spiral arms, past the halo of ancient stars, past the dark matter boundary where the galaxy's gravity finally loosens its hold and the number drops again. Not by half, not by an order of magnitude. In the intergalactic medium, the space between galaxies, the density of ordinary matter falls to roughly 1 atom per 10 cubic meters. Picture a box 3 meters on each side, 3 meters wide, 3 meters tall, 3 meters deep, a small bedroom. In that volume of intergalactic space, there is, on average, less than 1 atom, not 1 atom per cubic centimeter, not 1 per cubic meter. 1 per volume, roughly the size of the room you are in. And that already assumes you are in a region close to a galaxy where the density is slightly elevated by nearby structure. In the deep voids between galaxy filaments, the number drops further closer to 1 atom per 100 cubic meters, or 1 per volume the size of a large house. These are not poetic exaggerations. These are measured values from observations of how light bends through intergalactic space, how X-ray emissions distribute across galaxy clusters, how the cosmic web casts faint shadows on background radiation. The emptiness is real and it has been measured. And what the measurements show is that the intergalactic medium occupies a category of vacancy that has no equivalent anywhere in human experience. But here is what makes this stranger than it first appears. That near nothing, that 1 atom per 10 cubic meters of space, is not sitting still, it is hot, extraordinarily hot. The intergalactic medium in the filaments between galaxy clusters exists at temperatures between 100,000 and 10 million degrees. In some regions, considerably hotter. Physicists refer to this material as the warm, hot intergalactic medium, and it accounts for a substantial fraction, possibly close to half, of all the ordinary matter in the observable universe. Not in galaxies, not in stars, spread across the spaces between them, at temperatures that would vaporize any material object instantly, in a density so low that it is physically incapable of harming anything. That paradox takes a moment to settle. Temperature, in physics, is not the same thing as heat. Temperature measures the average kinetic energy of particles, how fast they are moving. Heat measures the total thermal energy transferred from one object to another, which depends not just on temperature but on how many particles are present to do the transferring. A spark from a campfire can reach temperatures of over 1,000 degrees and land on your skin without burning you, because there are so few particles in that spark that the energy transferred is negligible. The intergalactic medium is the most extreme version of that principle ever encountered. Particles moving at millions of degrees, meaning they are individually carrying enormous kinetic energy, but spaced so impossibly far apart that they almost never interact with anything. If you were somehow suspended in this material, no spacesuit, no protection, your body would not burn. The particles are too sparse to transfer any meaningful heat to your skin. You would die of something else, entirely radiation exposure over time, or the slow drain of your own heat radiating into a space so empty it returns almost nothing. The concepts of hot and cold require a medium. They require particles. They require contact. The intergalactic medium has the temperature without the medium, the heat signature without the heat. Where did this material come from? Most of it is primordial hydrogen and helium, left over from the first few minutes after the universe began, never gathered into galaxies, drifting in the large-scale structure of the cosmic web. Some of it was ejected from galaxies, gas blown outward by the cumulative energy of millions of supernovae, or driven by the radiation pressure of active galactic nuclei. The violent periods when the supermassive black holes at the centers of galaxies were actively consuming infalling material and releasing more energy per second than entire galaxies of stars. That outflow pushed gas past the galactic boundary, past the halo, out into intergalactic space, where it joined the diffuse medium and slowly became invisible. For decades, this material was called the missing baryons ordinary matter that cosmological models predicted should exist, but that telescopes couldn't find. The models were tracking the universe's total ordinary matter budget and finding that what could be observed in stars, in galaxies, in gas clouds, accounted for only about half of what the math required. The rest was apparently absent. It was not absent. It was between the galaxies, at temperatures high enough to be nearly transparent to the instruments that were looking for it, spread thin enough to produce no visible emission, requiring X-ray telescopes and careful analysis of how it absorbs specific frequencies of light to finally be mapped. The universe had hidden roughly half of its ordinary matter in a phase of existence sparse, hot, structureless, that fell between the categories scientists were searching. There is a lesson in that which extends beyond astrophysics. What is absent from our instruments is not always absent from reality. The intergalactic medium is the largest reservoir of ordinary matter in the universe, and it spent decades being invisible simply because the conditions of its existence didn't match the conditions we were equipped to detect. It was hot when we were looking for cool gas. It was diffuse when we were calibrated for dense structures. It was between things when our categories were built around things. The universe contains more than we can see. Not as a consolation, not as a way of suggesting hidden wonders waiting to be found, simply as a structural statement. Our instruments sample a slice of physical reality, and what falls outside that slice remains present whether we measure it or not. The intergalactic medium was there long before we had the tools to find it, filling the spaces between galaxies with heat without warmth, with matter without substance, with temperature without the possibility of touch. Now consider what it means that this near vacuum, this 1 atom per 10 cubic meters, this ghost of a medium is what connects galaxies to each other. Not highways, not bridges, not the continuous fabric that the word between implies. A medium so thin that particles within it travel for millions of years before encountering anything. A medium that is the closest thing the universe has to pure geometric space, distance without content, extension without substance. The space between galaxies is not a gap waiting to be filled. It is filled with almost nothing. And that almost nothing is the dominant state of matter in the observable universe, more voluminous than all the galaxies combined, more abundant than all the stars, stretching across the cosmic web in filaments that glow faintly in X-rays if you know how to look, and are otherwise as close to invisible as anything in physical reality has ever been. Which raises a question about what fills the spaces within those filaments, the voids inside the web itself, where even this near nothing becomes rarer still, where the density drops to its absolute floor, and where the universe displays its emptiness without apology or mitigation. Pull back far enough, and the universe stops looking like a collection of objects. It starts looking like a structure. Not a random scattering of galaxies adrift in space, not dots on a black canvas placed without order, but a specific, repeating geometry that covers the entire observable universe. A web of thin filaments connecting dense clusters at their intersections, surrounding vast empty regions that are themselves bounded by more filaments, which connect to more clusters, which border more voids, at every scale we can measure. The pattern repeats from tens of millions of light years to billions. It is the largest structure in the observable universe, and it was not assembled the way a structure usually is. No architect designed it. No force pushed matter into this arrangement deliberately. Gravity found it. To understand how, you need to go back to the beginning, not to the moment of the Big Bang itself, but to the first fraction of a second afterward, when the universe was a near uniform plasma of unimaginable density and temperature. And near uniform is doing a lot of work in that sentence. Not perfectly uniform, slightly uneven. Quantum fluctuations, the irreducible randomness built into the fabric of physics at the smallest scales, had imprinted tiny density variations across the early universe. Some regions were, by an almost unmeasurable amount, fractionally denser than others. The difference was something like 1 part in 100,000, not 1%, not 1/10,000th, 1 part in 100,000. For the first several hundred million years, almost nothing happened. The universe expanded, it cooled, the plasma thinned, and gravity, patient in a way that has no human equivalent, began to work on those tiny density variations. Regions that were fractionally denser had fractionally more gravitational pull. They attracted surrounding matter slightly faster than average. That increased density increased the pull further. More matter fell in, increased the density more, increased the pull more. Over hundreds of millions of years, that 1 in 100,000 variation grew slowly at first, then faster as the density contrast deepened into the first structural distinctions in the universe. Regions that were noticeably denser than average, and regions that were noticeably emptier. The denser regions eventually became filaments and clusters. The emptier regions became voids. But here is what makes this process stranger than it sounds. The ordinary matter, the hydrogen and helium that would eventually form stars and galaxies, could not have done this alone. In the early universe, ordinary matter was coupled to radiation. Photons and matter interacted so frequently that matter couldn't simply fall toward a density peak without the radiation pushing back, counteracting gravity's pull. The result was an oscillation, matter falling inward, radiation pushing it out, a pattern of acoustic waves moving through the early universe like sound through a dense medium. If the universe contained only ordinary matter, those oscillations would have prevented the dense filaments from forming quickly enough to match what we observe today. The structure would be smoother, the voids shallower, the web less defined. Something else had to be present. Something that felt gravity but did not interact with radiation. Something that could begin collapsing toward the density peaks immediately, without waiting for the radiation pressure to ease, building up the gravitational scaffolding before ordinary matter was free to follow. That something is what physicists call dark matter, and it outweighs all the ordinary matter in the universe by roughly 5-to-1. What it is, precisely, remains one of the genuinely open questions in physics. It is not made of atoms. It does not emit or absorb light at any wavelength that any instrument has detected. It does not interact through the electromagnetic force that governs almost every interaction you have ever experienced. It interacts gravitationally, and it interacts through what physicists call the weak nuclear force, the same force responsible for certain kinds of radioactive decay, though even that is not certain. Every direct detection experiment, running for decades in underground laboratories, shielded from cosmic rays, looking for the faint recoil that a dark matter particle would leave when colliding with an ordinary nucleus, has returned no confirmed signal. And yet the cosmic web is there. And the cosmic web cannot exist not in the form we observe, not with the filament structures and void distributions that surveys have mapped across billions of light years, without something providing the gravitational scaffolding in the early universe before ordinary matter was free to collapse. The web is not direct evidence of any particular dark matter candidate, but it is evidence that something with mass and no electromagnetic interaction shaped the large-scale structure of the universe from the beginning. Whatever it is the dominant form of matter in the cosmos, more abundant than everything in every star and galaxy combined. The filaments of the cosmic web are not uniform. They vary in thickness, in density, in the number of galaxies running along them. The densest intersections where multiple filaments meet accumulate the most material and produce the largest galaxy clusters, some of them containing thousands of galaxies bound together by gravity within a region a few million light-years across. The Virgo cluster, the nearest major cluster to the local group, sits about 60 million light-years away and contains more than 1,300 galaxies. The Coma cluster, farther out at roughly 320 million light-years, contains over 1,000 galaxies and is one of the densest structures in the nearby universe. Between those clusters, running along the filaments, galaxies trace the underlying dark matter distribution the way foam traces a current in water. They mark where the density is highest without constituting the density itself. The luminous matter, all the stars, all the gas, all the galaxies, is the surface indicator of a structure mostly invisible, mostly dark, mostly beyond any direct instrument we currently possess. When astronomers map the cosmic web using gravitational lensing, measuring how the mass of intervening structures bends light from background galaxies, they find filaments containing enormous concentrations of mass in regions that appear nearly empty in optical images. The matter is there. It does not glow. It does not absorb at visible wavelengths. It reveals itself only by the way it curves space around it, by the tiny distortions it imprints on the shapes of distant galaxies seen through it. The map of the cosmos drawn by lensing looks different from the map drawn by counting galaxies. The lensing map is the more complete one. There is something worth sitting with in that distinction. The idea that the universe's dominant structural component is something we know primarily through its absence from our instruments rather than through any direct contact. We have mapped the cosmic web in extraordinary detail. We know its statistics, its geometry, its evolution over cosmic time. We know how it shapes the formation and fate of every galaxy within it. We understand the mechanism by which it grew from quantum noise in the early universe to the largest organized structure in the observable cosmos. And the substance doing most of this work remains, after decades of searching, unidentified in any fundamental sense. Not because the physics is unclear. The gravitational behavior is well understood and extraordinarily well tested. Not because the evidence is weak. The evidence comes from 6 independent lines of observation at different scales and different epochs of cosmic history, all pointing to the same conclusion. But because what dark matter is made of, what particle, what field, what mechanism sits at the edge of what current physics can reach, the skeleton of everything visible in the universe is something we cannot see. It organized the galaxies, shaped the voids, connected the clusters, and built the architecture in which every star that ever burned did its burning. It was there before the first star formed. It will be there after the last one goes dark. And the voids it left behind, the regions where even dark matter is sparse, where the web thins to nothing, and space opens into something approaching pure emptiness. Those voids are not empty in the way a gap between objects is empty. They are empty in the way that silence is not merely the absence of sound, but a thing with its own weight, its own presence, its own particular quality that you notice more the longer you stay inside it. In 1981, a team of astronomers mapping galaxy positions in the constellation Boötes found something that should not have been there. Or rather, they found something that was not there, where galaxies should have been. They had been surveying a region of sky, measuring redshifts to calculate distances, building a 3-dimensional map of how galaxies distributed themselves through that volume of space. What they expected was the rough statistical scatter that surveys of the time had come to anticipate: galaxies more or less distributed, clustering somewhat, thinning somewhat, but present throughout. What the data returned was a sphere roughly 330 million light-years in diameter, containing approximately 60 galaxies. A typical region of that size, in an average part of the universe, would contain something in the range of 10,000. The Boötes Void had 60 galaxies in a volume where 10,000 were expected. That is not a gap, not a thin region, not a statistical fluctuation around a lower-than-average count. 60 out of 10,000 is a reduction of 99.4%. If you were standing in a stadium of 10,000 people and all but 60 of them vanished simultaneously, you would not describe the result as a quiet crowd. You would describe it as emptiness with 60 exceptions. The Boötes Void is emptiness with 60 exceptions. When the discovery was announced, there was a genuine period of scientific uncertainty about whether the measurement could be correct. Voids had been found before, regions thinner than average, underdense pockets in the web, but nothing approaching this scale or this degree of emptiness. Robert Kirshner, part of the team that made the discovery, described it as a hole in the universe. The phrasing was informal, but it was also accurate. Not a gap in a statistical sense, a structural absence of a kind that the models of the time struggled to account for. The cosmological question it raised was immediate. How do you empty a sphere 330 million light-years across? The answer connects back to what covered the amplification of early density fluctuations by gravity over billions of years. A region that was fractionally underdense at the beginning of structure formation had slightly less gravitational pull than its surroundings. Over hundreds of millions of years, matter that would otherwise have stayed nearby was instead drawn toward the slightly denser filaments and clusters at the void's boundary. The void did not actively expel matter. It simply failed to hold it. Gravity is not symmetric in that way. It concentrates, and where concentration happens, surrounding regions drain. The Boötes Void has been draining for roughly 10 billion years. Now consider what it means to exist inside it. Imagine a small galaxy, a dwarf galaxy, the kind of compact, dim structure that tends to populate void interiors, orbiting nothing in particular near the geometric center of the Boötes Void. On a planet in that galaxy, on a clear night, a creature with eyes looks up. The nearest significant concentration of galaxies is more than 165 million light-years away in any direction. For comparison, Andromeda, which we already established takes 4 billion years to reach, at our fastest speed sits 2.5 million light-years from us. The nearest galaxy cluster to a Boötes observer would be 66 times farther than Andromeda is from us. Not 66% farther, 66 times. The night sky from that vantage point contains almost nothing. No band of stars overhead the observer's own galaxy is too small and diffuse to produce a visible disk across the sky. No smudge of a nearby galaxy visible to the naked eye. No clusters of light in any direction that would hint at the existence of large-scale structure. The cosmic microwave background radiation would still be present, filling space with its faint microwave glow, but that is invisible to biological eyes, detectable only with instruments sensitive to wavelengths far outside the visible range. In visible light, there is effectively nothing. A civilization arising in that galaxy would look out at the universe and see a void. Not as a poetic description, as a literal observational fact. They would measure the sky, catalog the light sources, map what they could detect, and conclude that the universe is, in some fundamental way, empty. They would be correct about what they can see, and profoundly wrong about the actual structure of reality. The cosmic web, the filaments, the clusters, the superclusters, the architecture that spans billions of light-years and contains 2 trillion galaxies would be, for them, entirely invisible. Not because their instruments were insufficient, but because the nearest edge of that web is 165 million light-years away. The light from those structures is old and faint, and the statistical density of observable objects in their sky is so low that the pattern connecting them would be undetectable. A civilization in the Boötes Void might develop physics, mathematics, chemistry, astronomy. They might measure the cosmic microwave background and correctly infer a hot, dense beginning. They might calculate the expansion rate of the universe from the recession of the few galaxies they can detect. They might construct a cosmological model that is, in every way they can test it, accurate. And that model would be missing the most prominent organizational feature of the universe, the web that contains most of its galaxies, most of its structure, most of its observable matter. Not because they reasoned poorly, because their location gave them an unrepresentative sample, because the universe they could observe was genuinely, measurably emptier than the universe as a whole. That detail stops me in a way I find difficult to fully articulate. Not because it reflects badly on the hypothetical civilization they would be doing exactly what any honest observer does, drawing conclusions from available evidence, but because it illustrates something about the relationship between observation and truth that goes beyond astronomy. What we can measure from where we stand is not the same as what exists. The gap between those two things is not always closable. No matter how sophisticated the instruments, if the limitation comes not from the instruments, but from the position. We are not in the Boötes Void. We live in a relatively dense region of the universe on the edge of the local void, a much smaller, underdense region, bounded by the local sheet where the Milky Way, Andromeda, and roughly 80 smaller galaxies cluster together. Our sky is comparatively rich. We can see the structure of the cosmic web, trace its filaments in galaxy surveys, map its voids, measure its expansion. We can observe Andromeda with our naked eye. We can count thousands of galaxies in a patch of sky the size of a grain of sand. We have a view of the universe that the boat's observer cannot have. Whether this constitutes luck depends on what you think the universe owes its observers. Physically, it constitutes a sample bias we cannot fully correct for. We know the web exists because we can see it from here. We know voids like Boötes exist because we can observe them from outside. We are, in this specific sense, in an epistemically advantaged position, able to see not just our region but, in some direction, the emptiness that other possible civilizations might see as everything. The void galaxies that do exist inside the Boötes Void are among the most pristine objects in the observable universe. Isolated for billions of years with no significant neighboring galaxies to interact with, they have undergone fewer mergers, experienced less turbulence, consumed less external gas. They form stars more slowly than galaxies in dense regions. They age more quietly. In some respects, they are the most undisturbed objects in the cosmos structures that have changed the least since the early universe, because the environment that usually drives change interaction, collision, the gravitational influence of neighbors has been almost entirely absent. They are fossils. Not dead, still forming stars, still evolving but evolving slowly, in a medium so sparse that the usual catalysts of galactic change are missing. A void galaxy's history is, in a sense, the history of what a galaxy becomes when left entirely alone. And the Boötes Void is not unique. After its discovery, astronomers looked for similar structures and found them throughout the universe. Voids are not rare. They are the dominant feature of the cosmic web by volume. The filaments and clusters that contain most of the galaxies occupy a small fraction of the universe's total volume. Most of the volume is void. Most of the universe, by spatial measure, looks more like Boötes than it looks like the Virgo cluster or the dense regions near us. The crowded places are the exception. The emptiness is the rule. And inside that emptiness, in dozens of known supervoids stretching hundreds of millions of light-years across, there are small galaxies holding what might be civilizations, each one looking out at an essentially empty sky, building a cosmology from the handful of objects within observable range, completely unaware that beyond their horizon, the universe has an architecture they will never see. Not because they are less curious, or less capable, or less persistent than we are, because the universe put them somewhere that hides most of itself from view. What we know is shaped by where we are. That is not a statement about the limits of science. Science has, from our position, done extraordinary work in mapping what exists. It is a statement about the universe's indifference to the completeness of any particular observer's picture. The universe does not arrange itself to be legible from any specific vantage point. It simply is what it is, and the view from inside depends entirely on the address. Everything you have seen so far, the cosmic web, the voids, the filaments, the clusters, the Boötes emptiness, the warm, hot medium scattered between galaxies, every single one of those structures was written in the first fraction of a second after the universe began. Not in outline, in detail. The specific locations of the Boötes Void, the Virgo cluster, the filament connecting the local group to the larger cosmic web, all of it traces back to density variations that existed when the universe was younger than 1 second old, smaller than any object you have ever held, and hotter than any temperature that has existed anywhere in the cosmos since. The large-scale architecture of everything was encoded then, in fluctuations smaller than a proton, and then spent billions of years being decoded by gravity into the structure we observe today. To understand how, you need to hold two things in mind simultaneously. The first is that the very early universe was almost perfectly uniform. Not approximately uniform in the way a calm lake surface is approximately flat. Uniform at a level of precision that has no everyday equivalent. Density variations of 1 part in 100,000. That means if you sampled any two regions of the early universe, their densities would differ by less than 1,000th of 1%. To a physicist looking at that distribution, it looked very nearly like nothing like noise at the limit of detectability, like a measurement error waiting to be corrected. The second thing is that those variations were not random in the way a shuffled deck of cards is random. They had a specific statistical character, a specific relationship between fluctuations at different scales that came from a process operating before the universe was even a single second old, a period called inflation, an extraordinarily rapid expansion of space in the very first moments, during which quantum fluctuations, the irreducible uncertainty built into physical reality at the smallest scales, were stretched from subatomic sizes to macroscopic ones, imprinting their statistical signature across the entire observable universe before settling into the near-uniform distribution that gravity would later amplify. Inflation ended. The universe was left with a specific pattern of density variations. And then, gravity began its work. Regions fractionally denser than average had fractionally more gravitational pull. They attracted surrounding matter slightly faster. Their density increased, which increased their pull, which attracted more matter, which increased density further. The feedback loop ran slowly at first. The universe was still dominated by radiation, which resisted compression, which limited how quickly the overdense regions could grow. But as the universe expanded and cooled, the radiation's influence waned, and matter began falling more freely toward the density peaks. The first structures appeared roughly 100 million years after the beginning, small, dense clumps of gas where dark matter had already begun to concentrate, pulling ordinary matter in behind it. The first stars formed in these clumps. They were massive, hundreds of times the mass of the Sun, burning intensely for only a few million years before dying in supernova explosions that seeded the surrounding gas with the first heavy elements: carbon, oxygen, silicon, iron. The universe before those stars contained only hydrogen, helium, and traces of lithium. Everything heavier was forged inside them and distributed by their deaths. The iron in your blood was not here at the beginning. It was manufactured later, inside stars that lived and died before the Sun formed, and scattered into the gas cloud that eventually became the solar system. The calcium in your bones, the oxygen in your lungs, the carbon in every cell, all of it passed through the interior of at least one star before reaching you. The early universe did not contain the raw material for complex chemistry. Stars built that material and then died to release it. That is not a metaphor. It is a causal chain with no missing links. Over the first billion years, the structures grew. Gas fell along the dark matter filaments, those invisible threads that had formed first, as dark matter is unaffected by radiation pressure and could begin collapsing earlier. Galaxies assembled at the filament intersections where matter density was highest. Between the filaments, the underdense regions drained further, becoming the voids. The cosmic web emerged not from any external design, but from the amplification of a near imperceptible signal over astronomical timescales by a force gravity that never stops, that cannot be shielded or blocked, that acts across every distance at which matter exists. For the first several billion years, this process ran in one direction. Structures grew, filaments thickened, clusters accumulated mass, voids deepened. The universe was building complexity. Then something changed. Around 5 billion years ago, roughly when the solar system was just beginning to form, the expansion of the universe began to accelerate. This was unexpected in the most precise sense of that word. Physicists had assumed that expansion, having been set in motion by the Big Bang, would gradually slow that gravity, acting across all the matter in the universe, would gently decelerate the outward motion of everything. They were trying to measure how much it was slowing when two independent research teams, examining the brightness of supernovae and distant galaxies to calibrate the expansion rate at different epochs, found in 1998 that the expansion was not slowing at all. It was speeding up. Distant galaxies were receding faster than they should be. in a way that could only be explained by something actively pushing space apart, something with negative pressure, something that increases in total quantity as space itself expands, something that acts in the exact opposite direction from gravity. Physicists called it dark energy, which is a name for a measured effect, not an explanation of a mechanism. What dark energy actually is, what produces it, what physical field or property of space-time gives rise to it, remains one of the genuinely unsolved problems in fundamental physics. The most natural guess from quantum field theory, that it is the energy of empty space itself. The vacuum energy predicted by quantum mechanics produces a value roughly 1, followed by 120 zeros times larger than what is observed. That discrepancy, 120 orders of magnitude, is the largest mismatch between a theoretical prediction and a measured value in the history of science. Something in the theory is catastrophically wrong, or something is canceling almost all of the vacuum energy by a mechanism no one has yet identified. What we know about dark energy is only what it does. It constitutes roughly 68% of the total energy content of the universe. Dark matter accounts for another 27%. All ordinary matter, every atom in every star, every planet, every galaxy, every human body, every structure of any kind built from protons, neutrons, and electrons makes up approximately 5% of the universe's total mass energy budget. 5%. Everything we have ever seen, measured, touched, built, or described constitutes 5% of what exists. The remaining 95% divides between a substance that interacts only gravitationally and remains unidentified after decades of direct detection experiments, and a property of space itself that accelerates its own expansion in a way that no accepted theory adequately explains. The consequence of dark energy's acceleration is structural. As the universe expands faster, matter that is not gravitationally bound is carried away from everything else at increasing speed. Galaxies beyond the local group are receding. The filaments of the cosmic web are thinning as the space within them stretches. The voids are growing not just passively, in proportion to the overall expansion, but faster than average, because underdense regions have less matter to slow local expansion, and dark energy fills them as readily as it fills any other region of space. The structure that gravity spent billions of years building, dark energy is spending billions of years dissolving. Not quickly, not in any way that is perceptible on human timescales, or even on the timescale of civilizations, but the direction is clear, and it does not reverse. The cosmic web is temporary. The filaments will thin, the voids will expand. The clusters bound by gravity, the local group, the Virgo cluster, the structures held together by their own mass, will persist for a very long time, but they will become increasingly isolated as the expanding space between them and everything else grows beyond any causal contact. The universe wrote its architecture in the first second. Gravity spent billions of years building from those instructions. And dark energy, whatever it is, has been spending the last 5 billion years beginning to erase what gravity built, one filament at a time, at a rate that will increase without limit. The question this leaves open is not whether the dissolution will continue. The physics is clear that it will. The question is, what the universe looks like from inside that process, from the perspective of the structures that gravity built and that dark energy is slowly, permanently pulling apart, and what it means for anything within those structures to look outward and try to understand what is happening to them. Suppose, for a moment, that the engineering problem is solved. Not the fuel problem, not the materials problem, not the radiation shielding or the life support or the navigation. All of it solved. You have a spacecraft capable of sustained acceleration, of pushing its occupants to 90% of the speed of light and maintaining that speed across the intergalactic void. The technology works perfectly. The crew is healthy. The mission is launched. Now follow what actually happens. At 90% of the speed of light, the journey to Andromeda, 2.5 million light-years away, takes approximately 2.5 million years from the perspective of an observer watching from Earth. But time dilation compresses the experience duration for the crew. At 90% of light speed, time aboard the ship runs at roughly 44% of the rate it runs outside. The crew experiences not 2.5 million years, but approximately 1.1 million years of elapsed time. 1,100,000 years. That is not a journey that a civilization sends. That is a journey that swallows civilizations whole. The people who launched the ship are separated from the people who would arrive by a temporal gulf larger than the entire span of modern human existence. Our species has been behaviorally modern for perhaps 300,000 years. The crew arriving at Andromeda would be more than 3 times that span removed from the civilization that sent them. Whatever they were sent to do, whatever message they carried, whatever instructions they were given, all of it would be addressed to a world so distant in time that the concept of a return message becomes physically absurd. A reply traveling back at 90% of light speed would reach Earth another 1.1 million years after departure. The total round-trip communication lag, approximately 2.2 million years. The people who received that reply would be as remote in time from the mission's launchers as we are from the first humans who crossed into the Americas. And Andromeda, as established, is the nearest large galaxy. It is the closest destination of this kind. Go further to a galaxy at the edge of the local supercluster, say 60 million light-years away, and even with time dilation working in the crew's favor, the experience journey time exceeds 26 million years. There is no human continuity across 26 million years. There is no institution, no language, no genetic lineage, no cultural memory. The mission would depart from one species and arrive, if it arrived at all, as something else, shaped by millions of years of isolated evolution in a closed environment, related to its origin only in the way that we are related to the common ancestor we share with chimpanzees. The distance does not merely make the journey long, it makes the concept of a journey as a project with a sender, a traveler, and a receiver connected by shared identity incoherent at these scales. Now add the physics that was not in the engineering problem. Any object accelerating to near light speed faces the interstellar and intergalactic medium as an obstacle. At 90% of light speed, a hydrogen atom in the path of the ship is not a stationary particle to be dodged. It arrives at the ship with the kinetic energy of a high-speed cosmic ray. The intergalactic medium contains roughly 1 atom per 10 cubic meters of space, a vacuum so complete it would make any laboratory on Earth look crowded by comparison. Yet, at those speeds, each atom in the path of the spacecraft's forward cross-section arrives with enough energy to cause measurable damage to materials over long timescales. The thinner the medium, the less the problem, but across 2.5 million light-years of travel time, even 1 atom per 10 cubic meters adds up to an enormous total number of impacts. The energy required to reach 90% of light speed is not a rounding error. To accelerate 1 kilogram of mass to 90% of light speed requires approximately 38 petajoules of energy, roughly equivalent to the energy released by the atomic bomb dropped on Hiroshima, multiplied by about 900. To accelerate a spacecraft with enough structure to house and sustain a crew across a million-year journey, the energy requirements exceed the total energy output of the Sun across thousands of years. These are not obstacles that cleverness overcomes. They are not engineering challenges of the kind that were solved by going from propeller aircraft to jet engines. They reflect the fundamental relationship between mass, velocity, and energy. That special relativity describes a relationship in which the energy required to accelerate a massive object increases without limit as its speed approaches light, meaning that no finite energy budget closes the gap completely. The message that these numbers carry is not that the journey is difficult. It is that the journey redefines what a journey is. There is a second version of the problem that is quieter, but in some ways more final. Suppose you do not want to travel. Suppose you only want to communicate. Send a signal. A radio transmission aimed at a galaxy cluster 60 million light-years away, traveling at the speed of light, carrying whatever information you wish to transmit. The signal leaves. It travels outward at 300,000 kilometers per second. But the space it is crossing is expanding. The galaxy cluster it is aimed at is receding not by moving through space, but by having the space between it and you stretch. For galaxies within the local group, gravitational binding holds them in place against the expansion. For galaxies in the Virgo cluster, 60 million light-years away, the recession velocity due to expansion is approximately 4,000 kilometers per second. The signal is gaining on the target. Light moves at 300,000 kilometers per second. The target is receding at only 4,000, so the signal will eventually arrive. But it arrives at a galaxy that has moved substantially from where it was when the signal departed, and the signal itself arrives stretched. Expansion stretches the wavelength of any signal passing through it in proportion to how much the universe expanded during the signal's travel time. A radio transmission that left Earth 60 million years ago arrives redshifted, its frequency lowered, its wavelength lengthened, its energy reduced per photon. The amount of stretching depends on the expansion rate. For nearby targets, the shift is modest and correctable. For targets beyond a certain distance, the shift becomes severe enough that the signal, by the time it arrives, has been stretched into longer wavelengths carrying less energy per photon degraded, but still detectable in principle. For targets beyond the cosmic event horizon, those receding faster than light, the signal never arrives at all. The expansion of the intervening space outpaces the signal's progress, and the gap grows rather than closes. Any transmission aimed at a galaxy beyond that horizon is not just delayed. It is physically unable to reach its destination, regardless of how powerful the transmitter, regardless of how long you wait. The photons travel forever without closing the gap. That horizon sits at roughly 46 billion light-years from us in current comoving distance, a consequence of the universe's expansion history that means the observable universe extends farther than the distance. Light could travel in 13.8 billion years. But in terms of what we can actually communicate with going forward, what can receive a signal we send today, the relevant boundary is the Hubble horizon, at roughly 14 billion light-years, beyond which recession velocities exceed the speed of light. Anything beyond that line is already, in the practical sense of the word, gone. There is something clarifying about laying this out fully. Not to produce despair. Despair implies something has gone wrong, and nothing has gone wrong here. The universe is behaving according to consistent, well-understood laws. But those laws close certain doors, and they close them permanently, and they do not leave gaps for technology to find. The constraint is not on what we can build, it is on what the structure of space-time permits. Every civilization, wherever it sits in the cosmos, faces the same set of constraints. Whatever form intelligence takes in a galaxy 100 million light-years away, it is bounded by the same speed of light, the same expansion rate, the same energy requirements for relativistic travel, the same signal degradation across expanding space. The universe gives every observer the same rules and the same impossibilities. The isolation is not local. It is not a feature of our particular position. It is the structure of the universe applied uniformly to everything within it. Which means that whatever has ever lived anywhere in this cosmos, whatever has ever looked outward and wondered, whatever has ever sent signals or waited for replies, has been doing so inside a set of physical boundaries that made contact across intergalactic distances effectively impossible, regardless of how long they waited or how sophisticated their technology became. Not probably impossible. Physically impossible, in the precise sense that the mathematics of space-time assigns to that phrase. Whether that mathematics describes a universe indifferent to connection, or one that simply has no opinion on the matter, is a question the physics does not answer. In roughly 4 billion years, the night sky will change in a way it has never changed during the entire existence of our species. Andromeda will grow. Not suddenly, but over millions of years, the faint smudge that requires dark skies and patient eyes to find will expand. It will become unmistakable. Its oval shape will spread across more and more of the sky, its spiral arms eventually resolvable without instruments. A second galaxy hanging overhead as a permanent feature of the night, as familiar to whatever beings exist then as the moon is to us now. And then, over the following billions of years, it will stop being a separate thing in the sky. Andromeda is approaching at roughly 110 kilometers per second. At that closing speed, across 2.5 million light-years of distance, the collision, the first gravitational interaction between the two disks, is approximately 4 billion years away. Not 4 billion years until contact in any violent sense. Galaxies, as established, are mostly empty space. Stars are separated by such vast distances that two galaxies can pass through each other without a single stellar collision occurring. What happens instead is more subtle and more permanent. The gravitational fields of the two systems interact, distorting their shapes, stretching tidal arms of stars outward in great arcs, destabilizing the orbits of billions of stars and sending them onto new paths through the merged system. The process takes billions of years to complete. The galaxies will pass through each other, separate briefly, then fall back together under their combined gravity, pass through again, separate again, and slowly, over repeated encounters spanning perhaps 2 to 3 billion years, coalesce into a single structure. The result will not be a spiral. Both the Milky Way and Andromeda are spiral galaxies, but mergers of comparable mass spirals tend to produce elliptical galaxies structures without the organized disk and arms, smoother and rounder. Composed of stars moving in more random orbital orientations, the organized rotation of the original spirals scrambled by the violence of the merger. The merged galaxy, which has been informally called Milkomeda by astronomers running the simulations, will be an elliptical structure, quieter in its star formation than either of its parents, burning through its remaining gas more slowly, aging into something that looks less like the bright-armed spirals we see today and more like the ancient, red-tinted ellipticals that populate the centers of large galaxy clusters. The two central black holes, the Milky Ways, with a mass of roughly 4 million suns, and Andromedas, estimated at somewhere between 100 million and 150 million solar masses, will spiral toward each other as the galaxies merge. Gravitational interactions with surrounding stars will gradually drain energy from their orbits, causing them to spiral inward over timescales of millions to billions of years after the galactic merger is structurally complete. When they finally merge, the event will release gravitational waves, ripples in the fabric of space-time propagating outward at the speed of light in every direction, carrying with them the record of two supermassive black holes becoming one. No instrument we could build would survive to detect it. But the universe will record it regardless, in the background radiation of gravitational waves that permeates space. Where will the Earth be during all of this? Probably still here, in some form, for the early stages. The Sun will be entering the later phase of its main sequence life around the time the first gravitational interactions begin. In roughly 5 billion years, slightly after the merger's first close passage, the Sun will exhaust its hydrogen fuel and expand into a red giant, engulfing the inner planets. Whatever biological life exists on Earth by then, if any does, will not survive this transition. But the solar system itself, the Sun, the remaining outer planets, whatever debris field occupies the region of the inner planets, will persist as a gravitationally bound unit and will, in all likelihood, simply be relocated by the merger into a new orbital position within the combined galaxy. The probability of the solar system encountering another star closely enough to be disrupted is very small. The stars are too far apart, even during the merger. We will not be destroyed by the collision. We will be moved. The sky visible from wherever the solar system ends up within Andromeda will be unlike anything that has ever been visible from Earth. The familiar band of the Milky Way, the soft arch of our own galaxy's disk, visible on clear, dark nights as a diffuse river of light, will no longer exist in that form. Instead, the sky will be filled more uniformly with stars from the merged system, denser in some directions, thinner in others, without the organized disk structure that currently makes our galaxy identifiable as a band. The night sky will be brighter overall, richer in stars, but stripped of the familiar architecture that has been overhead since before our species evolved. That detail sits with me in a way I didn't expect when I first spent time with it. The Milky Way overhead, that specific arch, that specific distribution of light, is something that has been present in the sky of this planet for longer than complex life has existed on its surface. Whatever looked up from Earth across the last 500 million years saw, in some form, that same band. It was there when the first fish developed eyes capable of detecting it. It was there when the first land animals looked skyward. It was there throughout every chapter of human prehistory, visible to every human who ever lived before artificial light obscured it. And in 4 billion years, it will be gone not by catastrophe, but by merger, by the slow gravitational embrace of our nearest neighbor. Now move further into the future, past the merger, past the formation of Andromeda, past the red giant phase of the Sun, several billion years further. The universe outside the local group, outside the gravitationally bound cluster of galaxies that includes the Milky Way, Andromeda, and their satellite galaxies, is continuing to recede. The expansion of space is carrying everything beyond our gravitational neighborhood further away, accelerating as dark energy's influence grows relative to the thinning matter density. Galaxies that are currently visible are moving toward and eventually past the cosmic event horizon, the threshold beyond which their recession velocity exceeds the speed of light, and no future light they emit will ever reach us. The number of galaxies visible from Andromeda will decrease. Not abruptly, not within any time span a civilization would notice, but over billions of years, the observable universe as seen from our location will contract. Distant galaxy clusters will redshift past detectability, their light stretched to wavelengths too long for any instrument to capture efficiently, then stretched further still until individual photons arrive so rarely and carry so little energy that they are indistinguishable from background noise. The cosmic web, visible today in galaxy surveys spanning billions of light years, will fade progressively from view. Structures that currently allow us to understand the large-scale architecture of the universe will slip beyond the horizon one by one, taking with them the observational evidence that they ever existed. A civilization living in Andromeda several trillion years from now will look outward and see almost nothing. Their instruments will be sophisticated, whatever physics and technology have become across that timescale, but the raw data available to them will be impoverished in a way that ours is not. They will be able to observe the stars within their own galaxy, the remnants of the merger, the aging stellar population of an elliptical system gradually burning through its last reserves of star-forming gas. But beyond the galaxy, the sky will be dark in a way that ours is not. The cosmic microwave background, the faint afterglow of the Big Bang that currently permeates every direction of the sky at a temperature of 2.7 degrees above absolute zero, will have been redshifted further by the continued expansion cooler, its photons arriving less frequently, eventually dropping below any practically detectable threshold. And here is the thing that I find most difficult to hold clearly. Those future scientists, working carefully with the data available to them, might construct a cosmological model. They might measure the expansion rate of space from the recession of the few detectable objects at the edge of their observable range. They might calculate the age of the stars within their galaxy, infer a stellar formation history, develop theories about how their galaxy came to be. They might be rigorous, creative, careful, but they will not be able to detect the cosmic microwave background. That signal, the single most important piece of evidence that the universe began in a hot, dense state. The evidence that gave us the Big Bang model, the evidence that constrains the age and composition of the universe, will have been diluted and redshifted beyond reach. They will have no direct observational access to the early universe. And without that, the conclusion that the universe began, that it has a finite age, that it expanded from an initial state, becomes a hypothesis without the primary observational support that we take for granted today. We live in the era when the evidence is still readable. The universe's history is written in light that is still arriving. The cosmic microwave background still fills our sky. The distant galaxy clusters are still visible. The cosmic web is still mappable. The entire observational foundation on which modern cosmology rests is currently accessible in this particular window of cosmic time, because the universe has not yet expanded enough to erase it. In a few trillion years, the erasure will be complete. Not by destruction, not by any catastrophic event, simply by the expansion of space, carrying the evidence past the horizon, stretching the signal into silence, removing from the observable sky the very data that tells the story of the beginning. The universe is, right now, still telling us where it came from. That window does not stay open forever. The voids are not static. That is easy to miss, because the timescales involved are so far outside human experience that the voids appear fixed permanent features of a stable architecture, the blank spaces between the filaments of the cosmic web, the way silence fills the space between notes in a piece of music. But silence in music does not expand. The voids do. Consider what is happening right now, at this moment, across the universe. Matter in underdense regions, the voids, the spaces between the filaments, has less gravitational pull than the surrounding structure. The filaments and clusters, being denser, attract material from the voids faster than the voids can replenish it. Matter drains outward along the density gradient, flowing from the emptiest regions toward the threads and nodes of the cosmic web. The voids are not merely empty. They are actively being emptied. Their remaining matter pulled steadily toward the edges, leaving behind volumes of space that become incrementally more vacant with every passing million years. At the same time, the expansion of space is accelerating, providing a repulsive effect that grows stronger relative to matter as the universe ages. In dense regions, gravity is strong enough to hold structures together against the expansion. Galaxy clusters, the local group, the Virgo cluster, these remain gravitationally bound. But in the voids, where matter density is already close to nothing, the expansion encounters almost no resistance. The voids expand faster than the cosmic average. They are, in a measurable and ongoing way, the fastest growing structures in the universe. So two processes run simultaneously in the same direction. Gravity drains the voids from the inside. Dark energy stretches them from the outside. The result is a universe whose structure is becoming more extreme with time, not more uniform, as one might expect from expansion, but more contrasted. The dense regions are getting denser, because matter flowing out of the voids has to go somewhere, and it goes to the filaments and clusters. The empty regions are getting emptier, because they are losing material and expanding simultaneously. The cosmic web is not dissolving into smoothness. It is sharpening, filaments thinning, but growing more defined against the expanding backdrop of void. Clusters accumulating more mass at the intersections, the whole architecture stretching and concentrating at the same time. This will continue, and it will not reverse. There is a number that carries the full weight of this direction. Dark energy currently constitutes approximately 68% of the total energy content of the universe. Dark matter accounts for roughly 27%. All ordinary matter, Every atom, in every star, every planet, every body of water, every human being, every structure ever built adds up to approximately 5%. 5% of the universe is the stuff everything we have ever known is made of. The other 95% is either a form of matter that does not interact with light and has not been directly detected despite decades of experiments, or a property of space itself that we cannot explain, and whose theoretical prediction is off by 120 orders of magnitude from its measured value. That is not a small gap in understanding. That is a statement about how much of reality falls completely outside our current conceptual framework. We can measure dark energy's effects with high precision. We can calculate what it is doing to the expansion rate, predict how the voids will grow, model the future of the cosmic web with confidence. But what it actually is, what physical mechanism produces a constant energy density throughout space that increases in total quantity as space expands, remains, after decades of theoretical effort, an open question with no accepted answer. The universe is being actively reshaped by something we cannot explain. Not in a distant or hypothetical sense, right now. The expansion is accelerating right now, measurably, at a rate consistent with a cosmological constant, the simplest mathematical description of dark energy that has held steady for at least several billion years of observational data. Every galaxy not gravitationally bound to ours is receding slightly faster than it was a billion years ago. Every void is slightly larger than it was a billion years ago. The architecture that gravity spent the first 8 billion years of the universe building is being dismantled, slowly and without any apparent mechanism that connects to the rest of physics. There is a particular quality to this that I find difficult to fully articulate, not the scale of it, which can be stated in numbers, but the asymmetry of it. The universe spent the first several billion years building structure from almost nothing. From quantum fluctuations, 100,000 times smaller than the density variations, you would need to see a difference. Gravity assembled the entire cosmic web, every filament and cluster and supercluster we can map. That construction took billions of years and required the precise coordination of dark matter collapsing early, ordinary matter following, gas cooling into the first stars, heavier elements building up through stellar deaths, second-generation stars forming with rocky planets, chemistry developing complexity over geological timescales. The dismantling requires none of that coordination. Dark energy does not need to organize anything. It simply fills space, all space, equally, without preference for density or structure, and because it fills space, and because space is expanding, there is more of it every moment. It is not working against the structure the way a force pushes against a wall. It is working underneath the structure, expanding the floor, increasing the distances between everything that is not held together by its own gravity. The voids grow because there is nothing in them to resist the growth. The filaments thin because their ends are being pulled apart by the expansion of the void regions on either side. The direction of the universe is toward more emptiness. Not eventually, not in some distant theoretical future now, incrementally, at a rate that can be measured from the brightness of distant supernovae and the recession velocities of galaxy clusters. The universe that exists today is emptier than the universe that existed 5 billion years ago, and the universe 5 billion years from now will be emptier still. The process has no mechanism by which it reverses. What makes the voids worth understanding is not that they are dramatic. They are, by definition, featureless. And nothing dramatic happens in a region containing 1 atom per 100 cubic meters. What makes them worth understanding is what they represent about the direction of everything. The voids are the future of most of the universe's volume. As expansion continues and the filaments thin and the clusters become more isolated, the fraction of the universe's total volume occupied by voids grows. The structure that currently makes the cosmos feel organized, mappable, pattern that structure is concentrated in a decreasing fraction of total space, surrounded by increasing volumes of near nothing. We live in one of the dense regions. On the edge of a local void? Yes, but within the local group, within the larger structure of the Laniakea supercluster, within a filament of the cosmic web. We are in the part of the universe where matter accumulated, where gravity won locally, even as dark energy began winning globally. The fact that we exist here, in a dense region rather than in a void, is not a coincidence of any anthropic significance. It is simply that complex chemistry, planets, and biology require density gradients, require the stellar nucleosynthesis that only happens inside stars, require the gravitational conditions that concentrate matter into the structures where those processes occur. Life, as far as we know, is a product of the dense regions. The voids, however vast, offer nothing that chemistry can work with. The universe is becoming more like its voids than like its filaments. Not on any timescale a civilization would notice. Not within the span of a species or a geological era, or even the remaining life of the sun, but the direction is clear and the physics does not reverse it. And so what we are seeing when we map the cosmic web today is a snapshot of a process midway through its arc, the phase when structure still dominates the sky, when the filaments are still thick enough to contain thousands of galaxies, when the voids are still bounded by visible walls of light. Later, the walls will be thinner. Later still, they will be gone. And the question that follows from watching this process is not what will the universe look like when it is emptier. The question is what it means that the architecture dark energy is slowly dissolving the filaments, the clusters. The entire mapped structure of the cosmic web is also the only architecture in which anything capable of asking that question has ever been known to exist. There is a bridge between the Milky Way and the Virgo cluster. Not a bridge in any visual sense. You cannot see it, cannot point to it in the night sky, cannot photograph it with an ordinary telescope. But it is there, a filament of dark matter and diffuse gas stretching roughly 60 million light-years, connecting our local supercluster to one of the nearest dense concentrations of galaxies outside it. Matter flows along this filament very slowly, drawn by the gravitational gradient between the underdense regions flanking it and the denser nodes at either end. It has been there, in some form, for billions of years. And right now, without any announcement, without any measurable event on human timescales, dark energy is stretching it. Not breaking it, not yet, just stretching it, adding new distance to the space through which it runs, thinning the density of the gas and dark matter threaded along it, reducing the gravitational gradient that holds it together, making the flow of matter along it slightly slower than it was a billion years ago. Every filament in the cosmic web is undergoing the same process simultaneously. The web is not collapsing and it is not exploding. It is being gently, persistently, irresistibly pulled apart at the seams. The nodes, the clusters, and superclusters where gravity is strongest hold together, because the gravitational binding energy of a structure like the Virgo cluster, containing over 1,000 galaxies with a combined mass tens of millions of times that of the Milky Way, is more than sufficient to resist the expansion acting across its interior. But the filaments connecting those nodes do not have that luxury. A filament is not a bound structure the way a cluster is. It is a region of elevated density along which matter is in transit, and the expansion of space is lengthening the transit route faster than the matter can travel it. Think of it as a supply line being stretched behind a moving front. The front, the cluster, stays in place, held by its own gravity. The supply line, the filament, extends back through expanding space. At some point, the line becomes too long to sustain the flow that built the cluster in the first place. New material stops arriving. The filament does not snap, it just thins and fades, until the density along it drops below the threshold where it can be distinguished from background. The cluster does not know this has happened. It simply stops growing. This is the mechanism by which dark energy is dismantling the cosmic web, not through any dramatic event, but through the patient erosion of the connections between things. The structures themselves persist. The isolation between them deepens. There is a human analog to this that is imprecise but clarifying. Consider what happens to a network when the connections between nodes are gradually weakened without the nodes themselves being destroyed. The nodes, cities, institutions, clusters of people remain. Their internal coherence may even increase as resources that once flowed outward along the network begin to accumulate locally. But the network as a whole loses its function. Information that used to propagate across it now stays local. Patterns that depended on long-range connection dissolve. What remains is a collection of isolated concentrations, each internally rich, each increasingly unaware of what the others are doing, each unable to affect or be affected by the others. The cosmic web is undergoing exactly this process at scales of hundreds of millions of light years over time scales of billions of years. The Laniakea supercluster, the large-scale structure within which the Milky Way sits, a region roughly 500 million light-years across, containing the mass of approximately 100 million billion suns, is not a gravitationally bound structure. This is a fact that took time to absorb when I first encountered it clearly stated. Laniakea is defined by the pattern of galaxy flows within it. All the galaxies within its volume are moving, right now, toward the great attractor at its center, a dense region dominated by the Norma cluster and the Centaurus supercluster. But the gravitational pull of that attractor is not strong enough to hold the supercluster together against the expansion of space. The outer galaxies of Laniakea will eventually be carried away by the expansion before they complete their infall. Laniakea will not collapse into a single structure. It will dissolve at its edges while its inner core condenses, producing a smaller but more tightly bound remnant and a surrounding region of galaxies that simply drift away. What remains bound is determined by a specific threshold. Whether the gravitational binding energy of a structure exceeds the work that dark energy does in stretching it apart. Structures below a certain mass and density will not survive indefinitely. Structures above that threshold, dense galaxy clusters, the local group will persist as isolated islands, bound by their own gravity, surrounded by expanding voids, increasingly cut off from any material that might have fed them had the expansion been slower. The galaxies within those surviving clusters will not be destroyed. They will simply be all that remains visible from the inside of a cosmos that once extended 2 trillion galaxies across 93 billion light-years of observable space. The light bridges that currently connect us to the wider universe, the photons still arriving from distant galaxy clusters, the faint signals of the cosmic microwave background, the redshifted evidence of the large-scale structure are not permanent. They are the last transmissions of a connected era, still arriving because they were sent billions of years ago when the sources were closer and the expansion was slower. New light sent by those same sources today will never arrive because the expansion has carried those sources past the point from which light can close the gap. The connection is already broken in the causal sense. We are still receiving the echo of a relationship that no longer exists in any functional way. There is something specific about this that distinguishes it from ordinary loss of contact, the kind that happens when a signal degrades, or a civilization falls silent, or a species goes extinct. Those are events. This is geometry. The disconnection is not caused by anything going wrong. No failure, no catastrophe, no decision. Just the continued expansion of space, which is a property of the universe that has been operating since the beginning and will continue operating without any mechanism that reverses it. The bridges between structures are being removed not by force, but by the stretching of the medium through which they run. We are not watching this happen in any direct sense. The timescales are too vast for observation across human history. What we are doing is measuring the current state of the expansion, the current density of the filaments, the current recession velocities of the galaxy clusters at the web's nodes, and extrapolating forward using the physics that has been tested with high precision. The future of the cosmic web is not speculation. It is a calculation whose inputs are well constrained and whose output is a single direction, toward greater disconnection, sustained indefinitely at an accelerating rate. The filament connecting the Milky Way's local structure to the Virgo cluster will not be there forever. Neither will the filament beyond Virgo that runs toward the Perseus-Pisces supercluster, nor the one that connects that structure to the Coma cluster. Each connection in the cosmic web has a finite remaining lifespan, determined by the balance between its local gravitational binding energy and the rate at which dark energy is stretching the space it occupies. Some will last longer than others. None will last indefinitely. What gravity spent 8 billion years assembling from quantum noise, dark energy, is spending the next several 100 billion years quietly taking apart, not by undoing the structures themselves, but by severing the lines between them, one filament at a time, until each surviving cluster floats in isolation so complete that no signal it sends will ever reach another, and no signal from another will ever reach it. The universe is not moving toward unity. It is moving toward a state in which every remaining structure is perfectly, permanently, and physically alone, not as a consequence of any tragedy, but as the straightforward endpoint of a geometry that has been trending this direction since dark energy began to dominate approximately 5 billion years ago. The only remaining question is what those isolated structures will look like from the inside, what the sky will show to anything still present within them, once the last filament has faded and the last evidence of connection has been stretched beyond any possible detection. Start with the best version of the dream. Not a crude rocket, not a chemical propulsion system dragging its own fuel mass across the void. The best version, a spacecraft with sustained acceleration, elegant engineering, capable of pushing a crew to 90% of the speed of light and maintaining that velocity across the full 2.5 million light-years to Andromeda. The fuel problem is solved. The radiation shielding holds. The life support systems function without failure across the entire journey. Every engineering challenge that currently lies between us and such a machine has been overcome. Now follow what the physics actually does to the mission. At 90% of the speed of light, the Lorentz factor, the number that describes how dramatically time, length, and mass-energy relationships shift at relativistic velocities, equals approximately 2.3. This means that for every 2.3 years passing outside the ship, 1 year passes inside it. The journey to Andromeda, 2.5 million light-years at 90% of light speed, takes roughly 2.8 million years from the perspective of anyone watching from Earth. But aboard the ship, with time dilation compressing the experienced duration, the crew lives through approximately 1.2 million years of elapsed time. 1.2 million years. That number is not a travel inconvenience. It is not a challenge that better technology could reduce, because the time dilation is not a product of slow engines, it is a product of the speed itself, and the speed is already at 90% of light. The only way to reduce the experienced journey time further is to go faster, which requires more energy in a relationship that grows without limit as velocity approaches light speed. At 99% of light speed, the Lorentz factor becomes approximately 7. The experienced journey time falls to roughly 350,000 years. At 99.9%, the factor approaches 22. The experience time falls to around 110,000 years. Each step closer to light speed requires an order of magnitude more energy and still delivers a journey measured in hundreds of thousands of years. There is no speed at which the journey becomes biologically survivable for a continuous individual. This is the first way the physics breaks the mission, not through any engineering limitation, but through the sheer magnitude of the distances involved combined with the constraints that special relativity places on the relationship between speed, time, and energy. The crew that departs is not the crew that arrives, not because they age, but because across 1.2 million years of experienced time, every biological and cultural thread connecting them to their origin is severed by duration alone. The second way the physics breaks the mission is more subtle and, in some ways, more final. Consider the energy required. To accelerate 1 kilogram of mass to 90% of the speed of light requires kinetic energy of approximately 38 petajoules, roughly the energy released by detonating 900 weapons of the scale used at Hiroshima. A spacecraft capable of sustaining a crew of any size across a million-year journey needs structure, life support, propulsion, radiation shielding, and fuel reserves that add up to a mass measured in thousands or millions of kilograms at minimum. Scale the energy requirement accordingly. The total energy needed to accelerate a crewed interstellar vessel to 90% of light speed exceeds the total energy output of the Sun across several thousand years, and that assumes 100% efficiency in converting fuel to thrust, which no physical engine achieves. No civilization in its current form produces anything approaching that energy budget. A civilization that would be, by any reasonable definition, unrecognizable as continuous with the one that began the project. The third failure is the one that receives the least attention, perhaps because it is the quietest. Suppose the engineering is somehow solved, the energy somehow gathered, the ship somehow built and launched. The crew departs. From outside the ship, 2.8 million years pass. The civilization that launched the mission does not persist for 2.8 million years. No human institution has persisted for 2,000 years in recognizable form. No language survives 10,000 years without becoming unrecognizable. 2.8 million years is the span between us and the earliest stone tools of Homo habilis, the first recognizable members of our genus. Whatever exists on Earth when the ship's light-speed communication arrives, confirming it has reached Andromeda, shares approximately as much cultural and genetic continuity with the civilization that sent it as we share with those early tool users. The mission arrives at a destination, but there is no one at the origin to receive the news in any meaningful sense. The civilization that built the ship and the civilization that, if any, still exists, receives the signal are connected by biological descent and shared physics, nothing else. The project completes. The connection it was meant to establish does not exist, because the connection requires continuity at both ends simultaneously, and time has consumed the origin while the ship was in transit. These three failures compound each other. They are not three separate problems awaiting three separate solutions. They are three expressions of the same underlying fact. The universe is very large. Light travels at a finite speed, and the combination of those two properties sets hard limits on what any object with mass can do across intergalactic distances. The limits do not soften with better engineering. They are embedded in the structure of space-time itself, in the equations describing how energy, mass, velocity, and time relate to each other, equations that have been tested with extraordinary precision and show no sign of containing any loophole that might make the journey more tractable. There is something worth being precise about here, because this is a place where imprecision often creeps in. The impossibility being described is not the impossibility of faster-than-light travel, which is a separate and more well-known constraint. The impossibility is subtler, even well below light speed, at velocities that special relativity permits and that no known physical law forbids. Intergalactic travel remains categorically incompatible with the kind of project a civilization might meaningfully undertake. Not because the speed is insufficient. 90% of light speed is an extraordinary velocity, but because the distances are so vast that even that speed, sustained perfectly, produces journey times that exceed the coherent lifespan of any civilization or biological lineage by orders of magnitude. The dream of crossing to another galaxy is not a dream that better rockets will eventually fulfill. It is a dream whose fulfillment would require redefining what we mean by the words civilization, journey, and arrival so completely that the original dream would no longer be recognizable in the result. A ship that leaves a civilization behind for 1.2 million years does not carry that civilization across the void. It carries the atoms that once belonged to it. And those atoms, having spent 1,000,000 years sealed in a metal vessel crossing intergalactic space, arrive at Andromeda as something that the origin could not recognize, shaped by pressures and experiences and durations that no culture, no memory, no institutional continuity could bridge different, not by design, not by catastrophe, but by the simple and relentless passage of time operating at the only scale at which intergalactic distances can be crossed. If the crossing of space is foreclosed by time, and the crossing of time by the nature of biology and civilization, what does it actually mean to send a message rather than a body, and whether a message, traveling at the speed of light through expanding space, faces its own version of the same wall? In 1929, an American astronomer working at an observatory in Southern California compiled measurements of the distances to a set of galaxies and compared them with the velocities at which those galaxies were moving away from us. The relationship he found was simple and immediately alarming. Every galaxy he measured was receding. Not some of them, all of them. And the recession velocity was proportional to distance. A galaxy twice as far away was receding twice as fast. 3 times farther was receding 3 times as fast, with a consistency that was not a statistical approximation, but a precise linear relationship extending across every direction of the sky. The universe was expanding, not the galaxies flying outward through space like shrapnel from an explosion, but the space itself, stretching every point in the cosmos, moving away from every other point, the distances between all unbound structures increasing simultaneously, without any center, without any edge. That observation, now called Hubble's law, after Edwin Hubble, who compiled the definitive data, carries an implication that takes longer to arrive than the initial surprise. If recession velocity is proportional to distance, and if the expansion is ongoing, then there is a distance at which the recession velocity reaches the speed of light. Not the speed of any object moving through space that limit holds, and nothing with mass crosses it. But space itself is not an object. The expansion of space is not motion through space. It is the stretching of the medium in which motion occurs, and that stretching has no built-in speed limit. The same physical law that prohibits a particle from moving through space at the speed of light says nothing about how fast space can expand. These are governed by different equations describing different phenomena, and confusing them, treating the expansion speed limit as the same as the particle speed limit, is one of the most common errors in thinking about cosmological distance. The distance at which recession velocity equals the speed of light, given current measurements of the expansion rate, sits at roughly 14 billion light-years. Galaxies beyond that distance are receding from us faster than light, not moving through space faster than light. The space between us and them is increasing faster than light can traverse it. The distinction matters for a precise reason. A galaxy receding faster than light is not violating relativity. No local speed limit is broken anywhere in that process. The galaxy is, at every point in its local environment, at rest relative to its immediate surroundings. It is not moving quickly through anything. The space around it and around us is simply expanding, and the cumulative effect of that expansion across 14 billion light-years adds up to a recession velocity exceeding light speed. You can stand still and still be receding from something at faster than light speeds if enough space exists between you and that something, and all of it is expanding simultaneously. Now follow what this does to any signal we might send. A radio transmission leaves Earth at the speed of light, aimed at a galaxy cluster 60 million light-years away, within the range where recession velocities are manageable, where light can still close the gap over time. The signal travels. The target is receding, but slowly enough relative to the signal's speed that the gap closes. After 60 million years, the signal arrives. Aim further. At a galaxy cluster 500 million light-years away, the recession velocity at that distance, given an expansion rate of approximately 70 kilometers per second per megaparsec, where 1 megaparsec equals roughly 3.3 million light-years, is around 10,000 kilometers per second. The signal travels at 300,000 kilometers per second. It is still faster than the recession velocity. The gap still closes. The signal still arrives, redshifted and attenuated, but present. Aim at something beyond the cosmic event horizon, beyond the boundary where recession velocity exceeds the speed of light, currently at about 14 billion light-years in terms of objects we could reach with future light. The signal never arrives. Not because it slows down. Light does not slow down in a vacuum. The signal continues traveling at the speed of light through the space immediately around it, but the space between the signal and its destination is expanding faster than the signal can traverse it. The target moves away faster than the signal approaches. The gap does not close, it grows. The signal travels forever, literally, with no endpoint, gaining on nothing, closing no distance, carrying its message into a widening expanse that will never deliver it anywhere. There is a swimmer analogy that physicists use because it captures the mechanism precisely. Imagine swimming across a river whose current is faster than your maximum swimming speed. You enter the water and begin crossing. You are swimming as hard as you can, making forward progress relative to the water immediately around you. But the water is carrying you downstream faster than you can swim upstream. From the perspective of the far bank, you are moving away from it. You will never reach it, not because you stopped swimming, not because you tired, not because anything went wrong, because the medium you are crossing is moving in the opposite direction faster than you can move through it. A photon sent toward a galaxy beyond the event horizon is that swimmer. It moves through its local space at the maximum possible speed. The space it is crossing is carrying the destination away faster. The photon never arrives. This is not a communication problem that more powerful transmitters solve. The constraint is not on the signal's power or frequency or encoding. It is on the geometry of the space the signal must cross. A transmitter 1 trillion times more powerful sends photons at exactly the same speed, the speed of light, which is a fixed constant into the same expanding space, with the same result. The horizon is not a wall. It is a condition. The condition under which expansion wins over propagation, and it is set by the expansion rate and the signal speed, neither of which technology changes. There is a further subtlety that makes the situation stranger than it first appears. The observable universe, the region from which light has had time to reach us since the beginning, extends to a radius of approximately 46 billion light-years in current comoving distance. This is larger than 14 billion light-years because the space through which that ancient light traveled has itself been expanding since the light was emitted. Light that left its source when the universe was very young, when that source was much closer than 14 billion light-years, has been traveling through expanding space ever since, and the source has been carried far beyond the event horizon in the time it took that light to arrive. We receive that ancient light. We will receive no future light from that source. The connection is one way, and historical. We can see the record of what it was. But no new information from what it currently is will ever reach us. The universe presents us with a specific and peculiar kind of relationship to its most distant contents. We can observe their past but not their present, receive their history but not their current state, see where they were but have no access to where they are. The light arriving now from the most distant observable galaxies is a message sent billions of years ago, still in transit when those sources crossed the event horizon, completing a journey that began in a universe more compact than the one it is arriving in. These are not exotic edge cases. The majority of the 2 trillion galaxies in the observable universe are already beyond the event horizon for new light. Most of what we can see is something we can no longer reach, can no longer signal, can no longer exchange information with in any direction. The observable universe and the reachable universe are not the same thing, and the gap between them is growing as the expansion accelerates. Hubble's observation in 1929, that simple linear relationship between distance and recession velocity plotted on a graph at an observatory in California, was a measurement of the floor moving beneath everything. Not the ceiling, not a wall ahead. The floor itself, the space through which all motion occurs, expanding in all directions simultaneously, carrying the distant contents of the universe away from each other at rates that light cannot match across the largest scales. Every civilization in every galaxy faces the same floor. Every signal any of them has ever sent into intergalactic space has been traveling through the same expanding medium, subject to the same recession velocities, bound by the same horizon. The universe does not offer any observer a privileged vantage point from which the expansion looks slower or the horizon sits further away. The geometry applies uniformly. Every fire burning in the dark is, from every other fire's perspective, receding, most of them already beyond reach. What remains is only what is close enough that gravity, local, stubborn, refusing to yield, holds the floor still beneath it. A signal leaves Earth. Not a hypothetical signal, not a thought experiment, a real one. Since the early 20th century, electromagnetic radiation from this planet has been expanding outward in all directions at the speed of light. Radio broadcasts, radar pulses, television transmissions, the accumulated electromagnetic output of a technological civilization across more than 100 years, all of it radiating outward in an ever-expanding sphere. That sphere currently has a radius of roughly 100 light-years, meaning the earliest transmissions have now passed several hundred nearby star systems. But the signal is not what left. The signal that reaches a receiver 100 light-years away is not the signal that departed. Space has been expanding the entire time the transmission was in transit. Every wavelength in the signal has been stretched slightly by a factor determined by how much the universe expanded during the 100-year crossing. At 100 light-years, the stretching is negligible, a fraction of a percent, undetectable against the original encoding. But stretch the distance, and you stretch the effect. A signal crossing 1 billion light-years arrives with its wavelengths extended by roughly 7%. The frequencies are lower. The energy per photon is reduced. The information, encoded in the precise modulation of those frequencies, has been distorted by the expansion of the medium it crossed. This is not signal degradation in the ordinary engineering sense, the kind that better amplifiers or error-correcting codes can compensate for. The distortion is not random noise added to the signal. It is a systematic stretching applied uniformly to every wavelength present, a consequence of the universe expanding during the transit time. A receiver sophisticated enough to know the exact expansion history of the universe could, in principle, correct for it. But the correction requires knowing how much the universe expanded between transmission and reception, which requires knowing the distance and the expansion rate across that distance, which requires the receiver to already possess cosmological knowledge that the signal itself might be trying to convey. The problem is not unsolvable, but it is not trivial, and it worsens with distance. At distances of several billion light-years, the redshift becomes substantial. A signal originally transmitted in the radio spectrum, chosen precisely because radio waves travel well through the intergalactic medium, arrives shifted toward longer wavelengths. At a redshift of 1, meaning the universe has doubled in linear scale. Since the signal was emitted, every wavelength in the transmission has doubled. A signal encoded at a frequency of 1 GHz arrives at 500 MHz. The information survives, in principle, but the encoding is now in a frequency range the receiver was not expecting. If the receiver was designed to listen at 1 GHz, the signal passes through undetected. At a redshift of 10 reachable with signals sent toward the most distant observable galaxies, the wavelengths have been stretched by a factor of 11. A radio transmission arrives as something between microwave and shortwave radio, depending on its original frequency. At a redshift of 100, what was originally a radio signal arrives as an extremely low frequency wave, with wavelengths measured in kilometers, carrying so little energy per photon that distinguishing it from the thermal background of the universe requires instruments of extraordinary sensitivity. And all of this assumes the signal reaches its destination at all. There is a prior mechanism, the one that expansion uses to prevent signals from closing the gap to targets beyond the event horizon. But even for targets within that horizon, targets the signal can in principle reach, there is a subtler attrition that the physics imposes. The intergalactic medium is not a perfect vacuum. It contains sparse plasma, mostly ionized hydrogen at temperatures of hundreds of thousands to millions of degrees, at densities of roughly 1 atom per 10 cubic meters. That plasma is not dense enough to stop a radio signal, but it is not transparent to all frequencies. Very low-frequency radio waves are absorbed or reflected by plasma. The plasma frequency of the intergalactic medium, the threshold below which electromagnetic radiation cannot propagate freely, is extremely low by most practical standards, but a signal whose original frequency was already modest and whose wavelength has been stretched by a factor of 10 or 100 may find itself approaching or below that threshold at arrival, unable to propagate through the last portion of its journey. The universe degrades messages the way time degrades everything else. Not maliciously, not selectively, simply through the operation of physics on any signal passing through an expanding medium over sufficient distance and time. There is a detail here that I want to stay with, because it connects to something larger than the physics of transmission. A message is not just a signal. A message is a signal plus a receiver capable of recognizing it as meaningful. The physical delivery of a signal to a distant galaxy, even correcting for all the degradation, even assuming a powerful enough transmitter and a large enough receiver, does not constitute communication unless there is something at the destination that can interpret the arrival as an intentional transmission from an intelligent source, extract the encoding, and derive meaning from the structure it finds. Across intergalactic distances, with transit times measured in millions or billions of years, the probability that the civilization which sent the signal and the civilization which might receive it share enough common ground to bridge the encoding problem is essentially unknowable. Not because intelligence is rare, the argument does not require intelligence to be rare, but because a million years of independent evolution on different worlds, in different stellar environments, shaped by different physical histories, produces minds whose baseline assumptions about the structure of information may be as different from each other as our assumption that a sentence flows left to right is different from a system that encodes meaning in the pattern of spaces rather than the characters. Mathematics is often proposed as the universal language, the encoding that any sufficiently intelligent receiver would recognize, regardless of its biological origin, because mathematics is not a cultural convention but a description of physical reality that any observer of physical reality would be forced to derive. The argument has real weight. The ratio of a circle's circumference to its diameter is the same number in every galaxy. The relationships between prime numbers are the same everywhere. If any encoding survives cultural difference, mathematical structure has the best claim. But even granting this, even assuming a receiver intelligent enough to recognize a mathematical signal, sophisticated enough to correct for the redshift, patient enough to have been listening on the right frequency for the duration of the signal's transit, the message arrives as a record of what the sender understood millions of years before reception, not what the sender currently knows, not what they currently are. A message sent today about the structure of our solar system, the composition of our atmosphere, the mathematics we have developed, the physics we have tested that message, arriving at a galaxy cluster 500 million light-years away, describes a civilization 500 million years in its past. Whatever that civilization became in the intervening half-billion years is not in the message. The message is a fossil. Communication, in any meaningful sense, requires something closer to simultaneity than intergalactic distances permit. A conversation requires that the state of each participant at the time of exchange be reasonably current, that what one party says reflects who they are now, not who they were a geological epoch ago. Across intergalactic space, that condition cannot be satisfied for any exchange that involves round-trip communication. The minimum round-trip time for a message to the Andromeda galaxy and back is 5 million years. Any exchange of information between us and Andromeda is not a conversation. It is the transmission of two independent historical records, each describing a civilization at a specific moment in the past, each unable to respond to or even know about the content of the other until millions of years after it was sent. The universe permits the transmission of messages across intergalactic distances, in a technical sense. It does not permit the conversation that the word message usually implies. What it permits is closer to what we do when we study ancient starlight, reading a record of what something was, knowing we have no way to ask a follow-up question, knowing that what we receive is the full extent of the exchange, knowing that the source may no longer exist in any form, recognizable as continuous with what sent the signal. Every photon arriving from a distant galaxy is a completed message from a sender who has moved on. Every signal we send into the intergalactic dark is a completed message to a receiver we will never hear back from. Not because the universe is indifferent to connection, the universe has no opinion on the matter, but because the distances are large enough, and the speed of light finite enough, and the expansion ongoing enough that the conditions for real-time exchange between civilizations in different galaxies do not exist anywhere in the physics we have measured. The message travels. The reply, if it ever comes, arrives addressed to something that no longer exists. And the question that follows from all of this, from the impossibility of travel, the futility of waiting for replies, the systematic degradation of every signal crossing the expanding dark, is not whether connection across these distances is worth attempting. The question is what it says about connection itself, that the universe was built in a way that makes it, at the largest scales, structurally impossible. Right now, Andromeda is moving toward us. Not drifting in the way a galaxy cluster recedes, with the expansion moving toward us, closing the gap, its light compressed to slightly shorter wavelengths by the approach, a blue shift against the universal tide of red. At roughly 110 kilometers per second, Andromeda is one of the few major galaxies in the universe whose motion is dominated by local gravity rather than cosmic expansion. The gravitational bond between the Milky Way and Andromeda is strong enough to overcome the expansion of space between them at their current separation. The floor is still moving, but here, at this scale, the two galaxies are swimming faster than the current pulling them apart. They have been approaching each other for billions of years. They will collide in approximately 4 billion years. 4 billion years is the age of the Earth, the full span of time from the first oceans to the first humans to this moment, repeated once in its entirety. In that time, the continents have rearranged themselves multiple times. The oxygen content of the atmosphere has risen and fallen through several distinct eras. At least 5 mass extinctions have occurred. The sun has burned through roughly half of its hydrogen fuel. 4 billion years is not an abstract large number. It is a duration with a specific, legible content. And that content is the entire history of complex life on this planet. The collision will take that long to arrive, and then it will take that long again to complete. The first interaction, the point at which the outer halos of the two galaxies begin to overlap, will happen somewhat before the disk collision, as the dark matter halos and the diffuse stellar populations at each galaxy's edge begin to feel each other's gravity. The disks themselves, the organized spiral structures containing the bulk of each galaxy's stars and gas, will first interpenetrate roughly 4 billion years from now. But interpenetrate is the right word, not collide in any ordinary sense. Galaxies are not solid. They are not even close to solid. The average distance between stars in the Milky Way disk is roughly 4 light years, 4 years of light travel between one star and the next. When two galaxies pass through each other, the probability of any two individual stars actually colliding is vanishingly small because the stars occupy a negligible fraction of the total volume. The solar system, if it survives the encounter, will most likely be carried onto a new orbital path within the merged system without any star coming closer than perhaps a few light-years, dramatic by interstellar standards, but not catastrophic for the planets. What will be violent, and what will be visible on the largest scales, is what happens to the gas. The gas clouds within each galaxy are not point objects the way stars effectively are. They are diffuse, extended structures occupying large volumes. When two galaxies interpenetrate, their gas clouds do collide directly, with the compression and shock heating that discrete stellar encounters avoid. Compressed gas cools and fragments. Fragmented gas collapses under gravity. Collapsed gas ignites nuclear fusion. The merger of two large spiral galaxies is, among other things, a trigger for one of the most intense episodes of star formation the universe produces, a starburst, in which new stars form at rates tens or hundreds of times higher than in a quiescent galaxy. The merger of the Milky Way and Andromeda will light up the combined system with blue-white massive stars, burning intensely for only a few million years before dying in supernovae that scatter heavy elements across the merged galaxy and light it from within with the brief brilliance of the most massive objects in the universe. For whatever exists on whatever worlds remain during those first passage events, the sky will be unrecognizable. Consider what it would mean to stand somewhere and watch. 1,000,000 years before the first disk interpenetration, Andromeda, currently a faint smudge requiring dark skies, will have grown into a structure visible in daylight, its spiral arms resolved without any instrument, spanning a substantial arc of sky. 1,000,000 years is 5 times the entire span of modern human existence. Whatever is present then to observe the sky will have had that long to watch Andromeda grow from its current faintness into something that dominates the night. There is a slowness to this that is its own kind of strangeness, not an event that arrives suddenly, but a transformation so gradual that no single generation would notice the change, yet so complete that a being transported from now to then would not recognize the sky they stood beneath. As the disks begin to overlap, the familiar band of the Milky Way, the arch of our own galaxy's disk, visible on clear nights, will dissolve into something more diffuse and more extreme. Stars from both galaxies will be visible in all directions. Tidal streams, arcs of stars flung outward from both systems by the gravitational distortion of the encounter, will stretch across the sky in great curves. The gas compression will have ignited star formation in both systems, populating the sky with star-forming regions far brighter than any currently existing in the Milky Way. The Orion Nebula, currently among the most dramatic features in the night sky, will have been joined by dozens of more luminous counterparts, born from the compressed collision zones. The galaxies will not merge cleanly in a single pass. The simulations show the process as a series of encounters. The two systems interpenetrate, pass through each other, separate briefly as their stars overshoot due to inertia, then fall back together under gravity, interpenetrate again, separate again with less relative velocity, fall back again, a damped oscillation playing out over roughly 2 to 3 billion years before the system settles into a single merged structure. Each pass scrambles the orbits of billions of stars further, gradually erasing the organized spiral patterns of both parent galaxies and replacing them with the more random orbital distribution of the merger product. The two central black holes, the Milky Ways, with a mass of approximately 4 million times the Sun's and Andromeda's, estimated at somewhere between 100 million and 150 million solar masses, will spiral inward as the merger proceeds. The mass difference is stark. Andromeda's central black hole outweighs the Milky Way's by a factor of roughly 35. As the two galaxy cores approach, they will orbit each other, losing energy through gravitational interactions with the surrounding stellar populations, spiraling closer over millions of years until they merge into a single supermassive black hole. That merger will release gravitational waves ripples in space-time, propagating outward at the speed of light in every direction. Any civilization sophisticated enough to detect them in any galaxy within range will register a burst of gravitational wave energy unlike anything produced by stellar mass black hole mergers. Two of the largest gravitational wells in the local group becoming one. The final product, the merged system that forms after the oscillations damp out and the stars settle into new orbits, will be an elliptical galaxy, not a spiral. The organized disk structure, the winding arms, the differential rotation that gives spiral galaxies their characteristic shape, all of it will be scrambled by the merger into a smooth, roughly spherical distribution of stars moving in more random orbital orientations. The structure has been called Andromeda in some discussions among astronomers modeling the outcome, a name that acknowledges both parents without privileging either. It will contain somewhere between 1.5 trillion and 2 trillion stars, the combined populations of both galaxies, plus whatever stars formed during the merger event itself. It will also be largely done with star formation. The starburst triggered by the collision will consume much of the available gas. What remains will be distributed through a system no longer organized for efficient star formation, no disk, no spiral arms concentrating gas into the narrow regions where self-gravity leads most efficiently to stellar birth. Elliptical galaxies tend to be old and red, populations of long-lived low-mass stars, the remnants of an earlier era of rapid star formation, now aging quietly with no significant new input. Andromeda will be, in this sense, a post-climactic structure, the aftermath of the last major collision available within the local group, gradually cooling, its star formation rate declining towards zero, its most massive stars already long dead. 4 billion years to arrive, several billion years to complete. And at the end of it, a single elliptical galaxy where two spirals once danced separately across the local group, one of them, on certain dark nights, just barely visible to the naked eye from the surface of a small planet in the outer Orion spur. The dance is not violent by the standards of what galaxies do to each other. It is not even unusual. Mergers of comparable mass spirals are common throughout cosmic history, and the local group has been building toward this one since long before the solar system formed. What makes it worth dwelling on is not the physics, which is well understood, but the specific nature of what is being transformed. Two separate identities, two distinct structures with distinct histories, distinct stellar populations, distinct central black holes becoming one permanent, undivided thing. After that, for whatever remains in the local group, there will be no second galaxy to look toward. Only the question of what the sky looks like once the merger is complete, and the rest of the universe has already begun to disappear beyond the horizon. Imagine standing somewhere, not on Earth specifically, but on any world within Andromeda, the merged elliptical galaxy that forms after the collision. The merger is complete. The tidal streams of stars have settled. The starburst is over, its blue-white massive stars having lived their brief millions of years and died. The combined system has relaxed into its final shape, a smooth, roughly spherical distribution of stars, mostly old and red, their light warm and subdued compared to the blue-white flare of star-forming galaxies. Step outside on a clear night. The sky is spectacular. Stars in every direction, not concentrated into a band the way the Milky Way appears from Earth, but distributed across the full sphere of the sky, denser in some directions toward the galactic center, thinner toward the outer edges, but present everywhere you look. The merged stellar population of two major spiral galaxies, somewhere between 1.5 and 2 trillion stars, fills the night from every angle. It is, by the standards of any night sky a human has ever stood beneath, extraordinarily rich. Now point a telescope outward, away from the galaxy, toward where other galaxies used to be. The Virgo cluster is gone. Not destroyed, its member galaxies still exist, still burning, still orbiting their common center of gravity. But the expansion of space has been carrying them away for billions of years since the merger completed, and the light they emit now will never close the growing gap between them and us. The ancient light from Virgo is still arriving photons that left those galaxies hundreds of millions of years ago, when the universe was younger and the expansion rate had not yet compounded to its current effect. But it is arriving redshifted, stretched, attenuated, and getting more so with every passing era. Eventually, even that ancient light will have all arrived. There will be no new light coming from Virgo. Its image will simply fade, not blink out, but dim continuously. The last photons arriving more and more rarely, each one carrying less energy than the one before, until the rate of arrival drops below any practical threshold of detection. The Coma cluster, gone the same way. The Perseus cluster, the Fornax cluster, the great walls and filaments of the cosmic web, all of them, by this point in the future, having slipped past the horizon. Not a single galaxy outside the local group's merged remnant will be detectable. The number of galaxies visible to the most powerful telescope that could be built within Andromeda will be the galaxy you are inside, plus whatever small satellite galaxies remain gravitationally bound to it, perhaps a few dozen dwarf systems absorbed into the halo during the merger or orbiting at large radii. That is the observable universe, from this vantage point, in this era. Not because the rest of the universe ceased to exist. It did not. Billions of galaxy clusters continue burning through their stellar fuel in every direction, each one isolated behind the horizon in its own expanding bubble of space, unreachable and undetectable. But they might as well not exist, for all the evidence that remains available to any observer within Andromeda. The universe will look, from here, like a single galaxy surrounded by infinite blackness. The cosmic microwave background, that faint afterglow that currently fills the sky in every direction at 2.7 degrees above absolute zero, whose temperature variations carry the imprint of the density fluctuations from the first few 100,000 years of the universe, will by this point have been further redshifted by the ongoing expansion. Its temperature will have dropped to a fraction of a degree above absolute zero. The wavelengths of its photons, already in the microwave range, will have been stretched to wavelengths of meters, and then tens of meters, and then hundreds. The energy per photon will have fallen to a level that places its detection at the very edge of what is physically meaningful. For all practical purposes, the last direct evidence that the universe had a beginning will have been stretched into silence. What remains observable is only what gravity has preserved. There is a specific quality to this situation that took me a long time to hold clearly, and it is different from the isolated civilization thought experiment about Boötes. A civilization in the Boötes Void is inside a large empty region within a universe that is globally rich with structure. They simply cannot see it from where they are. A civilization within Andromeda, in this far future era, is not in a locally empty region surrounded by a rich universe. They are in a universe that has, for all observational purposes, become locally empty everywhere. The richness is gone, not hidden, not merely inaccessible by distance, but gone from observability in a way that no instrument could recover, because the photons carrying the evidence of that richness will have finished their journeys and will not be replaced. The universe is not hiding itself. It has genuinely become, from the inside, a single galaxy, surrounded by nothing detectable. The stars within Andromeda will continue burning. The galaxy is not dead. The stellar era continues for a very long time beyond this point, with low-mass red dwarf stars living for trillions of years, far outlasting anything in the current stellar population. But the context in which those stars exist, the web of connections to other structures, the observable evidence of the universe's history, the signals arriving from other galaxies, confirming that other galaxies exist, all of that context is gone. The stars burn in isolation so complete that even the concept of isolation requires a contrast to mean anything, and the contrast has vanished. Any civilization present within Andromeda at this time would inherit a cosmological record from the past. If they had preserved the observations made in earlier eras, they would have records describing a universe of 2 trillion galaxies, a cosmic web extending across 46 billion light-years of observable space, a microwave background carrying the signature of the Big Bang. They could study those records. They could model the physics that produced them. They could understand, from historical data, that they are living in the dim aftermath of a far richer era. But they could not verify any of it from current observation. Every observational test that modern cosmology relies on the large-scale structure surveys that map the filaments and voids, the microwave background temperature variations that constrain the composition and age of the universe, the redshift measurements of distant galaxies that confirm the expansion rate, the supernova observations that revealed the acceleration, none of it would be available to them as live data. They would have to take the historical record on faith or reconstruct its validity through the internal consistency of the physics, trusting that the models describing the invisible universe are correct, because they derive from a time when the evidence was still present and the derivations were sound. This is a different epistemic situation from simply not knowing something. It is knowing that you once had access to evidence that is now permanently gone, knowing the specific mechanism by which it was removed, and understanding that no future observation will restore it. The universe has not become more mysterious in the way that a hard question is mysterious. It has become inaccessible in the way that the past is inaccessible. The events happened, the evidence existed, the observations were possible, and the window closed. The night sky of Andromeda, in this far future era, turned outward toward the void, is not a sky full of questions. It is a sky full of answers that arrived too late to be checked. The stars within the galaxy continue their slow clockwork. Low-mass red dwarfs, burning hydrogen at a fraction of the sun's rate, will persist for 100 times the current age of the universe before exhausting their fuel. The galaxy dims gradually, its most luminous members dying first, the surviving population shifting toward the cool red end of the spectrum, the whole system aging with a patience that makes the current era look frantic by comparison. Outside, there is nothing visible. Inside, there are still stars. And whatever is present inside this island of light, surrounded by a darkness that extends without feature or limit in every direction, sits with a question that no physics resolves: whether the permanent absence of evidence for a larger universe changes, in any meaningful sense, what the larger universe is, or only what can be known about it. The universe is not trying to hide its origins. It is simply expanding, and expansion does what expansion does. It stretches everything embedded in space, including the light that carries the record of how the universe began. There is no intent in this, no mechanism with a purpose, just physics operating uniformly, indifferent to what the stretching destroys. But what it destroys is specific and worth naming carefully. 380,000 years after the universe began, the cosmos crossed a threshold. Before that moment, it was too hot for atoms to exist. The energy density was high enough that any electron attempting to bind to a proton was immediately knocked free by a passing photon. The universe was an opaque plasma, light scattering off free electrons in every direction, unable to travel more than a short distance before being absorbed and re-emitted. nothing could see anything. The cosmos was a fog lit from within, bright and entirely unreadable. Then the temperature dropped below roughly 3,000 degrees, and the electrons settled. Protons captured them. Hydrogen atoms formed for the first time, and the universe became transparent. The photons that had been scattering continuously were suddenly free to travel, and they did, in all directions, carrying with them a snapshot of the universe at that precise moment of transition. A snapshot encoded not in visible light but in thermal radiation, whose temperature reflected the conditions of that era, whose tiny temperature variations mapped the density fluctuations that were already present in the matter distribution, the same fluctuations that would eventually be amplified into the cosmic web. Those photons have been traveling ever since. They are the cosmic microwave background, and they are still arriving, right now, from every direction of the sky simultaneously. Photons that have been in transit for 13.8 billion years are reaching Earth, carrying the imprint of the universe as it was 380,000 years after its beginning. The temperature variations in this radiation, measured at the level of 1 part in 100,000, are the oldest direct observational data available to any civilization anywhere in the universe. Nothing earlier can be seen with light, because before recombination, the universe was opaque. The cosmic microwave background is not just old, it is the oldest visible thing. And the expansion is stretching it toward silence. The process is gradual and has been ongoing since the photons were released. When they were emitted, their wavelengths corresponded to a temperature of roughly 3,000 degrees visible light, mostly orange and red. By the time they reach us today, the expansion of space has stretched those wavelengths by a factor of roughly 1,000. What was emitted as visible light has become microwave radiation, detected not by the eye but by specialized instruments sensitive to wavelengths measured in millimeters. The photons carry the same information they always carried: the same temperature variations, the same angular pattern of slightly denser and slightly emptier regions, but the encoding has been shifted far outside the visible spectrum. The expansion will continue shifting it. In the era of Andromeda, the wavelengths will have been stretched further still into radio waves, then into progressively longer wavelengths, the temperature of the background dropping from its current 2.7 degrees above absolute zero toward 1 degree, then a fraction of a degree, then a fraction of a fraction. The energy per photon will fall below any practical threshold for detection. The rate of photon arrivals already sparse, given that the background is spread uniformly across the entire sky, and the photons have been traveling for so long will drop further, until the average time between individual photon arrivals in a given detector becomes longer than any practical observation window. The signal does not switch off. It fades continuously, without a defined endpoint, approaching undetectability asymptotically, always technically present, always receding further from any instrument's reach. In practical terms, at some point in the future history of Andromeda, the cosmic microwave background will have been stretched so far and thinned so completely that no instrument built within the galaxy could detect it, not because the photons stopped existing, because the energy they carry has been spread across wavelengths so long and a volume of space so vast that the signal is indistinguishable from the thermal noise of the environment. With it goes the primary observational evidence that the universe had a beginning. Not all evidence the internal consistency of physics would survive. The laws governing nuclear reactions, the ratios of hydrogen and helium produced in the first few minutes, the mathematics of general relativity describing an expanding space-time, all of that remains intact in the physics itself, derivable from first principles without requiring any observation of the background radiation. A sufficiently sophisticated civilization could, in principle, infer the Big Bang from the physics alone, the way a geologist infers the history of a rock formation from chemistry and decay rates without needing to witness the original event. But the direct observation would be gone. The thing that gave us confidence in the model in the first place, the measurement of the background, the mapping of its temperature variations, the confirmation that the universe was once hot and dense and uniform and then became transparent at a specific moment, that empirical foundation would no longer be available for checking. Future physicists would be working from a theory whose observational anchor had been removed by the expansion of the space the theory describes. The theory might still be correct. The derivations might still be valid, but the ability to point at the sky and say, "Here is the direct evidence," would be gone. There is something specifically uncomfortable about this that goes beyond the loss of data. Science, as a practice, is not just a collection of conclusions, it is a method, a way of holding conclusions accountable to ongoing observation, of revising models when new data contradicts them, of building confidence through repeated, independent verification. The cosmic microwave background is not merely a historical data point, it is an ongoing check, available to any era in which it remains detectable, confirming that the model of the universe's origin is not merely internally consistent, but actually corresponds to something measurable in the sky. Remove that check, and the model continues to exist. But the relationship between the model and the observable universe changes in a way that is not easy to characterize with a simple word. Consider what a physicist working in Andromeda, long after the background has become undetectable, would face. They have inherited a cosmological model from past eras, a model built by civilizations who could measure the background, who could map the large-scale structure, who could observe the expansion directly through the redshifts of thousands of galaxy clusters. Those civilizations recorded their data. The records survive if the civilization was careful enough to preserve them. The future physicist can read those records. They cannot verify them, not through any new observation. Every empirical check that would allow an independent confirmation of the model has been removed from availability by the expansion. The future physicist is in the position of a historian working from documents whose originals are lost, whose physical evidence has been destroyed, whose only resource is the internal consistency of the texts and the coherence of the physical laws those texts invoke. The model may be correct, almost certainly is correct, if the records are genuine and the physics is consistent. But the pathway from the model back to independent observational confirmation has closed. This might seem like a narrow epistemological concern, something that matters to philosophy of science more than to the actual content of knowledge, but it connects to something deeper about what it means to understand where you are. We know we live in a universe that began in a hot, dense state roughly 13.8 billion years ago. We know this because we can measure the background radiation, observe the large-scale structure, detect the expansion, and find that all of these independent observations converge on the same model. The convergence is the confidence. The universe itself, through the light still arriving, confirms its own history every time we measure it. That confirmation is not merely reassuring, it is the mechanism by which the model is more than a story. Future civilizations inside Andromeda will have the story. They will not have the confirmation. The universe will have expanded the evidence past their reach, stretched it into wavelengths too long for any instrument, thinned it into a signal too weak to separate from noise, carried the last galaxy cluster behind the horizon before its ancient light could provide one more independent check on the model. And all of this will have happened not through any catastrophe, not through any failure to preserve records, but simply because the universe has a geometry, and that geometry has been running in one direction since the beginning. The expansion is not destroying the truth, it is destroying the evidence. And the distinction between those two things, between the universe as it actually is and the universe as it can be confirmed to be, is precisely the gap that grows, gradually and without reversal, as dark energy continues the work it has been doing for the last 5 billion years, and will continue doing for however long remains. The universe is approximately 13.8 billion years old. Stars will continue forming for at least 100 trillion years, a number so large that our current age represents roughly 1/10,000th of the way through the era of star formation alone. By the measure of stellar history, we are not just early. We are almost at the very beginning. The overwhelming majority of stars that will ever burn in this universe have not yet ignited. Most of the planets that will ever form have not yet coalesced. Most of the opportunities for chemistry, for complexity, for whatever follows from the right conditions held long enough, none of that has happened yet. And yet we are living in the era when the universe is most completely observable. Both things are true simultaneously, and the combination is strange enough to deserve careful attention rather than a quick nod of acknowledgement. To understand what most completely observable means, it helps to trace what has been lost already and what will be lost next. The universe's very first 380,000 years are permanently inaccessible to light-based observation. The cosmos was opaque during that period, photons scattering endlessly off free electrons, the universe itself a fog that no light could cross. What happened in that era can be inferred from physics and constrained by later observations, but never directly seen. That window closed at recombination and never reopened. The cosmic microwave background is the earliest direct observation available, a snapshot of the universe at 380,000 years old, still arriving, still detectable, still carrying the temperature variations that seeded the entire large-scale structure we have been tracing. It is available right now. It will not always be. Expansion is stretching those photons toward wavelengths too long for any instrument, thinning their energy toward undetectability, carrying the last evidence of the universe's hot, dense beginning toward a silence that has no reversal. The distant galaxy clusters are visible right now. Their light has been traveling for billions of years and is still arriving. Galaxies at the edge of the observable universe, 10 or 12 billion light-years away, are still sending us ancient light that carries information about their structure, their redshift, their distance data points that allow the expansion rate to be measured at different epochs, that allow the history of the universe's growth to be reconstructed, that confirm or constrain cosmological models built from first principles. That data is still arriving. In the far future era of Andromeda, none of it will be. The cosmic web, the filaments, the voids, the superclusters, is currently mappable across billions of light-years of observable volume. Galaxy surveys have charted its structure in 3 dimensions, tracking how matter concentrated into threads and how the spaces between them emptied out over cosmic time. That map is available right now, today, to anyone with access to the published data. In the era that follows, that map will be a historical record that can no longer be cross-checked against current observation. All of these windows, the microwave background, the distant galaxies, the large-scale structure, are open simultaneously right now for the first and only extended period in which they will all be open at once. This is what the privileged era means. Not that we are special in any metaphysical sense, not that the universe arranged itself for our benefit, not that intelligence was placed at the center of the cosmic story, but that the specific combination of conditions required for full cosmological knowledge, a universe old enough to have developed structure, young enough that the evidence of its beginning hasn't been erased, transparent enough that the cosmic background is detectable, not yet expanded so far that the galaxy clusters have all receded behind the horizon, describes a window of finite duration, and we are inside it. The boundaries of that window are not sharp. It does not open on a specific date and close on another. It fades in at one end, as the universe cooled and became transparent and the first structures formed, and it fades out at the other, as the expansion carries the evidence of structure and origin progressively past the horizon. But it is a window, and its central portion, the era when all the primary observational tools of cosmology are simultaneously available, spans a period that is cosmologically brief. We are inside that central portion right now. There is a selection effect built into this. and it deserves to be named rather than left implicit. Life, as far as we understand it, requires specific conditions. Stable stars, heavy elements produced by previous stellar generations, rocky planets with liquid water, long timescales for chemical evolution. These conditions are available during the stelliferous era, the billions and trillions of years during which stars are actively burning. They are not available in the very early universe, which was too hot and dense for complex chemistry, and they become progressively less available in the far future as stars exhaust their fuel and the stellar population shifts toward dim, cold remnants. Any civilization capable of observing the universe must, by necessity, exist during the stelliferous era. But within the stelliferous era, the window for full cosmological observability is narrower still. A civilization arising very early in the stellar era, when the universe was only 1 billion years old, when the first metal-rich stars were just beginning to produce the heavy elements needed for rocky planets, would find itself in a universe still assembling its large-scale structure, with the cosmic microwave background still relatively fresh and bright, but with galaxy formation still underway and the large-scale surveys not yet possible. A civilization arising in the deep future trillions of years from now, around one of the long-lived red dwarf stars that will outlast the Sun by 100 to 1, would find the microwave background undetectable, the distant galaxies gone, the expansion unobservable, because nothing remains to be redshifted against. The era in which full cosmological knowledge is accessible from observation corresponds roughly to the current epoch, a few tens of billions of years centered on the present, during which a civilization with the right instruments can simultaneously measure the background radiation, observe the large-scale structure, detect the expansion through galaxy redshifts, and reconstruct the history of the universe from its beginning to its likely trajectory forward. We are in that era. Not by coincidence in the mystical sense, but in the precise sense that the conditions required for life and the conditions required for cosmological observability overlap in the same period, and we are one of the forms of life those conditions produced. The universe did not create us to observe it. We arose from the conditions the universe provided, and those conditions happen to include the availability of the observational evidence needed to understand the universe's history. The alignment is real, even if its explanation is selection rather than intention. What follows from this is not comfortable reassurance. It means that the cosmological knowledge we have built over the last century is not merely our current best understanding, subject to revision as better data arrives. It is, in a specific sense, the fullest possible understanding that will ever be available to any observer from within this universe. Not because we have reached the end of discovery, there is an enormous amount we do not know, but because the observational foundation on which deeper understanding must be built is present now, in this era, and will not be present later. Future civilizations will inherit our records if we preserve them carefully, and may extend the theoretical framework far beyond what we have managed. But they will not be able to look at the sky and see what we see. They will not have direct access to the evidence we have direct access to. The universe is, right now, still showing what it is. The light of 13.8 billion years of history is still arriving. The cosmic microwave background is still whispering across every direction of the sky. The galaxy clusters are still visible at distances that allow the expansion rate to be measured at every epoch of cosmic time. The cosmic web can still be traced across the full extent of the observable volume. The record is still here, still arriving, still readable by anyone with instruments calibrated to the relevant frequencies and the patience to look. This will not always be true. The horizon is moving. Not quickly. By human standards, the changes are imperceptible within a lifetime, or a century, or even a geological era, but the direction is fixed, and the physics does not reverse. Each era that passes carries more evidence past the horizon and stretches more of what remains toward wavelengths too long to detect. The window is open now, and it is closing, and the rate of closing will increase as dark energy's dominance over the matter density continues to compound. There is a responsibility in this that I find difficult to state without making it sound heavier than I mean it. Not a moral obligation, not a command, just a fact of timing with a specific implication. The observations being made right now, in this era, with the instruments available in this century, are observations that will not be available for repetition. The light arriving today from a galaxy 12 billion light-years away is the last light from that particular moment in that galaxy's history that will ever reach us. The temperature measurement of the cosmic microwave background made today is a measurement of a signal that is incrementally weaker than it was yesterday, and incrementally weaker still than it will be tomorrow. Each observation is not merely a data point. It is a record made during the last era in which that record could be made at all. And what happens to everything that has been recorded, whether it persists, whether it is understood, whether it informs whatever comes next, that is the question that does not belong to physics alone. In the summer of 1950, a physicist eating lunch at Los Alamos turned to his colleagues and asked a question so simple it barely qualified as a question. If the universe is as old as we think it is, and if the conditions for life are as widespread as the numbers suggest, then where is everybody? Enrico Fermi did not write the question down. He did not present it at a conference. He asked it over food and probably moved on to something else within the hour. What he had no way of knowing was that the question would still be unanswered 75 years later, after decades of increasingly sensitive instruments scanning millions of stars, after surveys of over 10 million stellar sources using radio telescopes more powerful than anything available in 1950, after examining galaxies for the waste heat signatures that would indicate energy collection at civilizational scale, the galaxy remains silent. The search has not settled the question, it has sharpened it. To understand why the silence matters, you need to hold two numbers against each other. The Milky Way is approximately 13.6 billion years old. The time required for a civilization to expand across the entire galaxy, not at light speed, not with exotic propulsion, but using self-replicating probes traveling at a modest fraction of light speed and constructing copies of themselves from local material at each destination, is somewhere between 1 million and 10 million years. 1 million years is less than 1/100th of 1% of the galaxy's age. The implication is direct. If even a single civilization anywhere in the Milky Way had developed this capability at any point in the last several billion years, evidence of it should be detectable by now, everywhere, including here. The math does not require a fast civilization or an ambitious one. It requires only that one civilization, once, managed to survive long enough and develop far enough to begin expanding, and the galaxy has been running this experiment for long enough that the result, if it happened, would be unmistakable. The result is not unmistakable. The result is silence. Every proposed explanation for that silence carries a specific implication, and none of the implications are comfortable. If life itself is extraordinarily rare, if the origin of biology from chemistry is so improbable that it has happened only once or a handful of times in the observable universe, then we are nearly alone, and the weight of that aloneness is different from the theoretical isolation described earlier in this journey. That earlier isolation is a physical feature of the universe's geometry. The distances too large to cross, the signals too degraded to carry meaning, the expansion too persistent to bridge. That isolation applies regardless of whether other civilizations exist, but if life is rare, the isolation is compounded by the absence of anyone else to be isolated from. The universe is not a system in which connection has been made structurally impossible. It is a system in which, for the most part, there was never anything to connect with. If life is common but civilizations reliably destroy themselves or fall silent before becoming detectable, the great filter explanation, in which some transition in the development of intelligence is nearly impossible to survive, then the silence is a graveyard. The galaxy is not empty because nothing arose. It is empty because what arose did not persist. Whatever that transition is, whether it is the development of weapons capable of planetary sterilization, or the exhaustion of the resources needed for continued growth, or the convergence toward forms of existence that do not broadcast electromagnetic signals, or something we have not yet imagined, it claims civilizations reliably enough that their collective absence is the dominant feature of our observational sky. And if the great filter lies ahead of us rather than behind us, then the silence is a warning from the future about what happens to species like ours when they reach whatever threshold we have not yet crossed. These three possibilities do not exhaust the space of explanations, but they span the range from the moderately unsettling to the directly relevant. What they share is this: each of them makes the search for other intelligence not merely an exercise in curiosity, but something closer to a diagnostic. The answer to Fermi's question, wherever everybody is, tells us something about what the universe does with intelligence once it arises. And we do not know the answer. The search continues because of something that is worth examining directly rather than leaving as background texture. Humans are a social species, not in a casual or approximate sense, in the deep biological sense, that our nervous systems were shaped by millions of years of evolution on a planet where survival depended on group membership, where recognition of other minds was one of the most important cognitive capacities a developing brain could acquire, where the presence of other humans was so constitutive of normal existence that its absence registers as a specific category of distress distinct from other kinds of suffering. We did not choose to be social. The architecture was built into us long before we had the capacity to reflect on it. We carry that architecture into our relationship with the cosmos. The search for other intelligence is not, at its root, a strategic project, not primarily a search for allies, or for useful knowledge, or for confirmation that the universe is hospitable to life. It is something more immediate than that. It is the application of a social instinct to the largest possible scale, the extension of the impulse to find other minds into a space that the physics, as this journey has carefully documented, has made the finding nearly impossible. The impulse predates the physics knowledge. It runs deeper than any calculation about signal strength or expansion rates. We look because we are built to look for other minds, and the habit does not switch off at the edge of the solar system. This creates a specific tension that is hard to resolve cleanly. The universe, as this journey has traced it, is built in a way that makes persistent contact between civilizations in different galaxies physically impossible, and contact between civilizations in the same galaxy extremely difficult across the timescales that distinguish meaningful exchange from the coincidental arrival of ancient fossilized signals. Even optimistic assumptions about communication technology do not overcome the combination of expanding space, signal degradation, and the temporal discontinuity imposed by transmission times measured in millions of years. The universe is not hostile to connection. It is simply structured in a way that connection, at the scales we instinctively reach for, is not available as a feature. And yet we broadcast. Since the early 20th century, electromagnetic radiation carrying the encoded output of a technological civilization has been expanding outward from this planet in all directions at the speed of light. Not by deliberate decision, initially, the first radio broadcasts were not intended as interstellar messages, but as the unavoidable byproduct of using the electromagnetic spectrum for communication. Everything we have transmitted to each other across the surface of this planet, everything that leaked into space rather than being absorbed by the ground, has been propagating outward ever since. A sphere of unintentional signal, roughly 120 light-years in radius, centered on Earth. Within that sphere are several hundred star systems. If any of them hosts something capable of detecting the signal, they are, right now, receiving it. The signal is faint. By the time it reaches even the nearest stars, it has spread across a sphere so large that the power per unit area is extraordinarily small, well below the detection threshold of any instrument we currently possess, aimed at a star 40 light-years away. Whether a more sensitive receiver could detect it is an open question. Whether anything exists with a more sensitive receiver aimed at us is the open question. There is something worth being precise about in the human response to the silence. The silence is not proof that no one is there. Absence of evidence at the sensitivity levels of current instruments is not evidence of absence at all sensitivity levels. The search has been running for a cosmically negligible duration, 65 years of active listening, covering a fraction of the galaxy's stars and a fraction of the possible signal types. The silence so far does not tell us that the galaxy is empty. It tells us that if the galaxy contains other technological civilizations, they are either not broadcasting on frequencies and at power levels detectable by our current instruments, or they are broadcasting but we have not yet looked in the right direction at the right time, or they exist but are too far away for their signals to have reached us, or they have never existed. The data constrains the possibilities but does not resolve them. What the silence does, which is different from what it proves, is force a confrontation with a specific asymmetry in our situation. We are a species that evolved to seek connection. We live in a universe whose structure makes connection at the scales we instinctively reach for very difficult. The gap between what we reach for and what the physics provides is not a problem to be solved. It is a feature of the situation, as permanent as the expansion of space and as indifferent to our preferences as the finite speed of light. The question Fermi asked over lunch in 1950 was not really about physics. It was about whether we are alone in the way that matters, not merely alone as a physical consequence of the geometry of space, but alone in the sense that no other mind anywhere in the observable universe has ever looked up at the same darkness and asked the same question. The universe does not answer that question. It simply continues expanding, carrying the evidence of its own history past the horizon, stretching every signal into longer wavelengths, thinning the intergalactic medium to 1 atom per 10 cubic meters, building the architecture of isolation one filament at a time, preserving inside each gravitationally bound cluster the small fires that matter assembled for itself burning, for now, in what might be total solitude, or might be part of a larger pattern of burning that the distances and the silence have prevented us from seeing. We do not know which. We keep looking because not knowing is different from knowing the answer is no, and because the impulse to look is built so deeply into what we are that distinguishing it from curiosity, from hope, from the simple refusal to accept a silence as final is something the physics cannot do for us. Whether looking makes any difference to what is actually out there, whether the universe cares, in any sense, that something within it refuses to stop searching, that is a question with no available answer. Pull back far enough and the universe stops looking like anything you were taught to expect. Not a room full of galaxies, not a canvas scattered with stars, not the image from any deep field photograph, with its comfortable compression of impossible distances into something the eye can rest on. Pull back far enough past the local group, past the filaments of the cosmic web, past the scale at which individual galaxies resolve into distinct objects and become instead statistical components of a density field, and what remains is mostly nothing, punctuated at vast intervals by small concentrations of matter that burn for a while and then don't. Each of those concentrations is a galaxy. Each one is, from a sufficient distance, a campfire. Not in the poetic sense of a warm, inviting light, but in the precise physical sense. A small region where matter has locally defied the universe's dominant tendency toward diffusion, where gravity has held something together against the expansion that is pulling everything else apart, where nuclear fusion is converting hydrogen into heavier elements and releasing energy as light in the process. The fire is real, the warmth is real, and the darkness surrounding it, in every direction, for distances that everything traced in this journey has worked to make real, is also real. We have been inside one of those fires the entire time. Everything traced across this journey, the compression of photographs, the 100,000-year crossing of the Milky Way, the unreachable shore of Andromeda, the near vacuum of the intergalactic medium, the dark matter scaffolding, the Boötes Void, the quantum fluctuations of the first second, the mathematics of why nothing can cross to another galaxy, the slow collision of the Milky Way with Andromeda, the sky going dark in Milkomeda, the cosmic microwave background fading towards silence, the evidence of the beginning being erased by the expansion that followed it, the privileged era we are inside right now, the silence that answers Fermi's question at every frequency we have learned to listen on. All of it is a description of the fire we are in, and the darkness around it, and the fires we can see burning in the dark, and the ones we cannot reach, and the ones that burned before any of this and are already out. The darkness is not hostile. It has no opinion about the fires burning inside it. It does not arrange itself against them. It simply is what it is, the dominant state of the universe, by volume, by mass, by the direction that physics has been trending since dark energy began to accelerate the expansion 5 billion years ago. The darkness wins. In the end, in the only sense that matters physically, it occupies more and more of the total volume as the fires burn out and the voids expand and the filaments thin and the last gravitationally bound clusters become isolated islands with no visible neighbors and no way to confirm that the universe was ever anything other than a single galaxy surrounded by infinite dark. But not yet. Right now, at this specific moment in cosmic time, inside the privileged era we have been tracing, the fires are still burning, and the evidence of the universe's history is still arriving, and the cosmic web is still mappable, and the faint smudge of Andromeda is still visible on clear, dark nights to anyone patient enough to let their eyes adjust. The window is open. The light is still coming in. There is something I have been circling that I want to try to say directly now. At the end, without dressing it in science, it does not need. The universe built the conditions for its own observation. Not intentionally, not through any mechanism that resembles purpose, but causally, in the straightforward physical sense. The same processes that produce the cosmic web produce the stars, and the same processes that produce the stars produce the heavy elements, and the same processes that produce the heavy elements produce the rocky planets, and the same processes that produce the rocky planets produce the chemistry, and the same chemistry, given enough time and the right conditions, produced nervous systems capable of detecting patterns in light, and those nervous systems, given more time and the accumulated pressure of selection acting on variation, produced minds capable of measuring the expansion rate of the universe and reconstructing the density variations of the plasma that existed 380,000 years after the beginning. There is a line, completely unbroken by any non-physical step, from the quantum fluctuations of the first second to the observation of those fluctuations in the cosmic microwave background. The observer is made of the same physics as the thing being observed. The measurement is part of the system being measured. This does not make us important in any cosmic sense. The universe does not register our presence. The voids do not shrink because we measured them. The expansion does not slow because we detected it. The isolation does not ease because we named it. The fires burning in every galaxy across 2 trillion separate gravitational wells have been burning regardless of whether anything within them looked up and asked what they were. But it does mean something specific about what is actually happening right now, in this era, on this planet, in the minds of anyone who has followed this journey through to its end. The universe is, locally and temporarily, aware of itself. Not everywhere, not permanently, not in a way that changes what the universe is, but here, in this fire, in this brief window when the evidence is still arriving and the instruments are sensitive enough to read it and the minds interpreting the data are connected by language and mathematics to the results, Something is happening that did not happen in the first billion years of the universe's existence and will not happen in the last trillion. Matter organized in a specific way is comprehending the structure of the whole from inside a small piece of it. The campfire analogy does not break here, it deepens. A campfire does not know it is a campfire. It does not know the darkness around it extends for billions of light years in every direction, or that the darkness is mostly composed of dark energy and dark matter whose nature we do not fully understand, or that the fire itself is a local and temporary violation of the universe's dominant trend. A campfire burns without any of that context. We burn with it, and we know. Not everything, not even close to everything. The earlier acts were honest about what remains genuinely open. What dark matter is made of, what produces dark energy, whether anything else is looking out from any other fire across the cosmic distance that separates them from us, whether the evidence we are accumulating in this privileged era will survive in any form that can be used by whatever exists inside Andromeda when the sky goes dark and the background radiation fades. These are real, open questions, and the physics does not close them. But the structure of the universe, the distances, the emptiness, the expansion, the origin in quantum noise, the fate in accelerating isolation, that structure is known. Not perfectly, not finally, but in its broad features, in its causal chains, in the specific physical mechanisms by which 100,000 years of light travel, and 1 atom per 10 cubic meters, and the recession velocity of the Virgo cluster, and the temperature variations of the cosmic microwave background, and the merger trajectory of 2 spiral galaxies are all connected to the same set of underlying equations that is known, here, now, in this fire, by minds built from the same physics that everything else is built from. The darkness is vast. The fire is small. The knowledge is real. You have been carrying all of it quietly through this night, letting it settle in at whatever pace it needed, without being asked to feel any particular way about it, without any conclusions being drawn that the physics does not actually support. The universe is mostly empty. The fires are real. The isolation is structural, and it deepens. The evidence of the beginning is being erased by the expansion it produced. The era in which all of this is observable is finite, and we are inside it. None of that is made lighter by understanding it. But understanding it is what we do. It is what the fire does, in the particular configuration that produces minds like this one and like yours. And there is something in that, not comfort exactly, not resolution, but something in the fact that the darkness is not unexamined. That someone, somewhere in the thin filament where gravity held enough matter together long enough for biology to arise and biology to produce awareness, looked out at the 2 trillion campfires burning in the dark and began, carefully, to count. That is where we are. That is what this has been. Thank you for spending this time in the dark with all of it. For staying with the distances even when they stopped resolving into anything comfortable. For following the light from the first second to the last detectable photon without looking away. For sitting with the silence where Fermi's question echoes without an answer, and with the expansion that carries the evidence past the horizon whether or not anything is watching it go. The stars will be in the same positions tomorrow night. The cosmic microwave background will still be arriving from every direction, a little cooler than yesterday by a fraction so small it requires the most sensitive instruments we have ever built to measure. The Andromeda galaxy will be 2.5 million light-years away and 2.5 million years closer in transit time, its light still carrying the record of what it was before our species existed. All of that will be there. And so, for now, will you. Rest well. Good night.